Welcome back to Supernova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Before we set sail among the stars, we must first sense the shape of the ship that carries us. The Milky Way, in all its splendor, is built upon an invisible architecture. Like an elaborate cathedral shrouded in fog, its grand design is partly hidden from our eyes. What holds up this starlit city? What scaffold keeps our galactic home from flying apart? To answer, we venture beyond the visible, into the domain of the unseen, a realm of gravity and ghostly matter, the invisible architecture that underpins the galaxy. Imagine a vast, dark scaffold woven from something we cannot touch or see. A web of gravity, shaped by a mysterious substance known as dark matter. We call it dark, not just because it emits no light, but because it eludes direct detection, hiding in shadows beyond our instrument's reach. And yet, though invisible, it is immensely real. It sculpts the galaxy's form and governs the dance of the stars. If we could don magical glasses to see mass instead of light, we would behold a gigantic halo enveloping the Milky Way, a roughly spherical cloud stretching far beyond the galaxy's shining disk. This halo, mostly made of dark matter, is the invisible architecture, the foundation on which the visible Milky Way is built. We feel its presence through its pull. Just as a steady hand might guide dancers on a floor, the gravity of dark matter guides the stars in their orbits. In the outskirts of the galaxy, far from the brilliant core and spiral arms, stars and clouds of gas whirl around the center at astonishing speeds. Logic suggests they should drift away into the depths of space. There simply isn't enough visible mass in stars or gas to hold them. Yet, they remain bound, as if tethered by phantom strings. These tethers are the gravitational grip of dark matter, an unseen mass whose influence permeates the galaxy. It forms an invisible halo, extending hundreds of thousands of light years beyond the edge of the visible Milky Way, cocooning it like an unseen guardian. This hidden architecture doesn't glow or sparkle, but it makes itself known in other ways. Picture the galaxy like a vast, spinning carousel. In a normal carousel, things at the edge move more slowly than those near the center. But in our galaxy, stars in the far suburbs orbit at nearly the same speed as those closer in. It's as if the carousel's rim has extra hidden weight, providing the needed gravity to keep those outer stars from escaping. That extra weight is dark matter. It is the silent partner to all the shining stars, outweighing them many times over. For every star we see twinkling in the Milky Way, there is far more mass hiding in the dark, perhaps 5 to 10 times more. This dark mass forms the scaffold, the architecture without which the beautiful glowing disk of our galaxy would not exist as we know it. But dark matter is not the only component of the invisible architecture. Gravity itself is the architect, the master planner that molds matter into structure. Long ago, before the Milky Way even had its name or shape, gravity drew together a diffuse cloud of matter. It began to pull everything inward, spinning and flattening the gathering material. Like an artist shaping clay, gravity sculpted the first outlines of our galaxy. It made the wispy tendrils of primordial gas collapse into denser clumps, igniting the first stars. Over billions of years, it orchestrated mergers of smaller protogalaxies, each merger guided by the gravitational hand of dark matter, halos merging as well. The Milky Way grew within a gravitational cradle, an underlying framework stretching through space like the skeleton of a great beast. Even today, gravity's influence extends beyond the stars. The space between galaxies is not entirely empty. It is threaded by filaments of dark matter, forming a cosmic web. Our Milky Way lives at the intersection of these filaments, like a pearl caught in a spider's web of invisible threads. Through these threads, clumps of matter, both dark and ordinary, flow inward. One might imagine cosmic tides, slow and inexorable, delivering fresh gas and even small galaxies toward the Milky Way. This ongoing infall continues to shape our galaxy, guided by the unseen architecture of the cosmic web. We drift in a gentle current of gravity, a river whose banks are made of dark matter. Close your eyes and picture the Milky Way not just as stars, but as an enormous gravitational presence. Feel the invisible arms that extend far beyond the furthest star, reaching out into intergalactic night. This is the scaffold that holds us, the container of our existence on a galactic scale. Stars, nebulae, planets, and people all live embedded in this gravitational field, moving along paths choreographed by an architecture we perceive only indirectly. The invisible architecture humbles us. It reminds us that what is most important is often hidden. We live in the luminous beauty of a spiral galaxy, but that beauty is underwritten by something dark, massive, and enigmatic. The stars trust this structure. They orbit faithfully, generation after generation, as if following ancient roads built by an unknown engineer. We too are sustained by this invisible framework. Without it, our sun might wander off into the void, carrying Earth and us with it into solitude. Instead, we remain part of this grand rotating city of stars, anchored by a dark, unseen sea of gravity. As our journey continues, keep this concept close to your heart. Not everything that matters can be seen. The Milky Way's brilliance rests upon an invisible foundation. In life and in galaxies, the unseen often guides the seen. We move onward now into the visible realm of the Milky Way, but we do so knowing that an invisible architecture holds it all together, like the silent knowledge beneath spoken words, or the unseen wind shaping the dunes. In this galaxy, as in ourselves, there is more than meets the eye. Anatomy of the Milky Way. Now that we sense the hidden scaffolding, let us step back and behold the anatomy of the Milky Way, the grand design of our galactic home. If we could rise above the disk and look down from far away, what would we see? We would witness a spiral galaxy in its prime, a flat disk of stars and gas, with graceful arms winding outward from a bright central region. It would resemble a vast rotating pinwheel strewn with glittering lights. This is the city of stars we call home, a cosmic metropolis containing everything we know. At the center of it all lies the galactic bulge, a rounded hub of stars that swells above and below the flat plane of the disk. The bulge is like the city center, crowded, bustling, and ancient. Its stars are mostly old amber-colored beings, many billions of years in age. Some of these stars are almost as old as the universe itself, born when the galaxy was young and the cosmos had barely emerged from darkness. The bulge is roughly spherical or slightly elongated. In fact, observations show that the Milky Way has a central bar, a long horizontal concentration of stars crossing the core. Think of it as a glowing bar of stars at the galaxy's heart, with the bulge wrapped around it. This stellar bar acts like a cosmic traffic system, channeling gas inwards and helping to form new stars and feed the central region. The bulge and bar together form the beating heart of the Milky Way, densely packed with stars dancing in complex orbits. Extending outward from the bulge are the spiral arms, the most striking feature of a spiral galaxy. The Milky Way sports multiple spiral arms, curving out like swirls in a whirlpool. Each arm is a region of higher density. Imagine waves in the galactic disk, where stars and gas get slightly bunched together as they orbit the center. In these denser waves, gas clouds compress and new stars ignite, lighting up the arms with hot, young suns that shine blue-white. Nebulae, great clouds of glowing gas, pepper the arms, marking the nurseries where stars are born. From above, the arms would appear like starlit ribbons or the tendrils of a vast cosmic jellyfish rotating slowly around the core. They have poetic names derived from constellations we see in their directions: Perseus Arm, Sagittarius Arm, Scutum Centaurus Arm, Carina Arm, and the smaller Orion Spur where our Sun resides. Our solar system is currently nestled in this Orion Spur, a minor arm or branch between major arms, about 27,000 light-years from the galactic center, halfway out in the disk. We truly live in the galactic suburbs, a quiet neighborhood between busier spiral arms. The disk itself, which contains the spiral arms, is a marvel. A broad, thin plain of stars, gas and dust, roughly 100,000 light-years across in diameter. To give a sense of scale, that is about 1e5 light-years from one end to the other. In miles, a number so large, about 600 trillion, that it defies comprehension. Yet, despite its vast width, the disk is relatively thin, only about 1,000 light-years thick in the main stellar layer. In proportion, it's much thinner than a pancake. The Milky Way is a truly flat system. If the galaxy were reduced to the size of an old vinyl record, the disk would be like a razor-thin film, and the bulge a small bump at the center. Within this disk, stars orbit the center in nearly circular paths, like billions of bees swarming around a hive. They move in orderly fashion, although each carries its own slight up and down motion, giving the disk some thickness. There are actually two components to the disk: a thin disk containing most of the young stars, gas and dust, where spiral arms are prominent, and a thick disk of older stars that extends a bit further above and below the plane. The thick disk's stars are fewer and older, hinting at a past era of the galaxy when star formation and dynamics were a bit different. Together, these disks form the galactic equivalent of the streets and districts where our tale of star life unfolds. Encircling everything is the stellar halo, a spherical distribution of stars and ancient clusters that envelop the disk and bulge. The halo is sparse. Its stars are like lone wanderers, often old and feeble in light, scattered in a vast volume. Among them are the globular clusters, about 150 tight balls of very old stars orbiting the galactic center in extended, inclined paths. These clusters are fossils of an earlier time, some formed in the Milky Way's youth, others perhaps the remnants of small galaxies consumed by the Milky Way long ago. The stellar halo reaches far beyond the disk, fading into the dark. It's the galactic countryside, mostly empty, but for those isolated stars and clusters. As we learned in the invisible architecture, this stellar halo is just the visible tip of a much larger dark matter halo that extends even farther and holds the whole system in its gravitational grip. Imagine for a moment we could view a cross-section of the Milky Way, a side view. We'd see the bulge in the middle, a central swelling of stars. Stretching out from it is the thin disk, narrow and bright, with spiral arms embedded within. Slightly puffed up around the thin disk is the thick disk, a dimmer and broader spread of stars. Surrounding everything is the faint halo of ancient stars and globular clusters. This is the layered anatomy of our galaxy, a structure as intricate as any organism. Each part, bulge, bar, thin disk, thick disk, arms, halo, has its own character and story, yet all are bound together by gravity into one rotating system. Within this grand design, our Sun is a tiny speck. It takes about 250 million years for the Sun to complete one orbit around the galactic center, a galactic year. The last time we were at our current position in orbit, there were dinosaurs just beginning to roam Earth, and the first flowers were blooming. In that time, the Sun has journeyed around the galaxy perhaps 18 to 20 times in its 4.6 billion year life. This illustrates both the immense scale of the Milky Way and the surprisingly dynamic nature of our position in it. We are moving along with the entire solar system at roughly 230 kilometers per second, over 500,000 miles per hour, just to keep up with the galactic rotation, like riders on a massive carousel. The Milky Way's anatomy is not rigid. It's a living structure. The spiral arms rotate around the center, though not like solid blades. Stars drift in and out of them. The bar in the center slowly twists. The very disk can ripple. Interactions with satellite galaxies can send waves through it, causing subtle warps. In fact, observations show our disk is slightly warped, like a stretched-out ripple, likely due to gravitational interactions with neighbors or remnants of old mergers. So one might picture the Milky Way not as a static pinwheel, but as a swaying spiral, its disk breathing and waving over long timescales, its arms a pattern in motion. To truly appreciate this anatomy, consider the unity of it. Hundreds of billions of stars, each with its own orbit, many with their own planets, together forming these coherent structural components. From our vantage point on Earth, inside the disk, we see the Milky Way as that misty band across the sky. That band is essentially our edge-on view through the disk, a cross-section of countless distant stars concentrated along the plane. The dark patches we see, like the Great Rift dividing the bright Milky Way in the summer sky, are not empty of stars, but choked with dust that blocks starlight. Those are part of the disk's anatomy too, dark nebulae that silhouette against the starry backdrop. It is humbling to realize that for a long time, we didn't even know the true shape of our galaxy. Early astronomers peering with small telescopes, or just eye, only saw that band and tried to guess our imagely in the 20th century did we map the Milky Way's spiral structure, using telescopes sensitive to radio waves and infrared light, which can penetrate dust, and by cataloging the distances of stars and clusters. Today, missions like Gaia have measured precise positions and motions of over 1 billion stars, allowing us to cartograph the Milky Way's structure with unprecedented accuracy. Yet, being inside it, we still find pieces of the puzzle gradually, like a person mapping a forest from within, tree by tree. In summary, the Milky Way's anatomy can be thought of in layers and components. A luminous central bulge with a bar, a sprawling disk with spiral arms, thin disk plus a thicker disk of older stars, and a vast halo beyond. It is a majestic aggregation of matter and stars, structured yet fluid in form. Think of the Milky Way as a great cosmic tree. The bulge is the sturdy trunk. The disk and arms are the wide branches and leaves catching the light, and the halo is the sparse canopy spreading out into the sky. Or imagine it as an island. The bulge is a mountainous continent at the center. The disk is the flat expanse of land and sea around it with spiral currents, and the halo is the thin atmosphere and lonely outlying islets. This is our galaxy's body, magnificent and humbling. Knowing its anatomy, we are ready to delve deeper into its organs and processes. We have seen the map. Now we turn to the citizens of this galaxy, the stars themselves, and how they live and evolve in this stellar city. Stellar population and evolution. Every point of light in the Milky Way is a story in itself. A star shining with nuclear fire, perhaps orbited by planets, perhaps destined to explode or fade. In the Milky Way's vast population, there are stars of all ages and sizes, from brilliant blue giants to faint red dwarfs. Stellar population and evolution is the study of these billions of lives. How stars are born, how they age, and how they die, all within the galactic community. As we traverse this topic, imagine walking through a cosmic garden where stars are like flowers at different stages, buds, blooms, withering stalks, all contributing to the cycle of life in the galaxy. Astronomers classify stars in our galaxy broadly into populations. The population 1 stars are those like our Sun, relatively younger in cosmic terms, and richer in heavy elements, elements heavier than helium, because they are born from recycled materials. They tend to reside in the disk, especially the spiral arms, where active star formation is ongoing. Then there are population 2 stars, old, metal-poor stars, fossils from the early galaxy. These often inhabit the bulge and the halo, like in globular clusters or as solitary halo stars. There is even a theoretical population 3, the very first stars born in the universe, extremely metal-poor and long gone now. but their imprint might survive in some of the oldest Pop-2 stars. In the Milky Way, stellar evolution is not just theory, it's on full display. Consider the spiral arms. They are studded with stellar nurseries where new stars take shape. Giant cold clouds of molecular gas and dust, colossal wombs known as molecular clouds, collapse under gravity in pockets, forming clusters of newborn stars. Within these nebulae, we find young protostars still accreting mass, often hidden in dust, and bright newborn stars whose intense radiation causes the surrounding gas to glow. The Orion Nebula, for example, in our Orion Spur, is a nearby region where such processes occur, and the Carina Nebula is another dramatic stellar nursery, featuring massive stars that formed just a few million years ago. These newborn stars are typically hot and massive, shining blue-white and living short, brilliant lives. They are often found in loose groups or clusters, like cosmic kindergartens of stars. The presence of such O and B-type stars in the spiral arms is what makes the arms stand out with a bluish tinge. These stars are luminous beacons, but they burn out quickly in a few tens of millions of years, and thus never stray far from their birthplaces. As stars age, they drift away from such nurseries and join the general population of the galactic disk. Intermediate mass stars like our Sun live for billions of years, orbiting peacefully, slowly using up their hydrogen fuel. They may drift around the galaxy many times. Our Sun, for instance, has gone around the center about 20 times and witnessed the changing arrangement of spiral arms and clouds around it. Over time, stars like the Sun will exhaust their core hydrogen and expand into red giants, glowing with a cooler, reddish hue but enormously larger and more luminous than before. In this phase, they puff off their outer layers, enriching the surrounding space with elements formed in their interiors. Many such aging stars can be found in the Milky Way. Look toward the bulge, and you find myriad red giants crowding the region, evidence of older stellar generations. Some stars live violent, short lives. The high-mass stars, perhaps born in those same clusters, race through their nuclear fuel in mere millions of years. They swell into supergiants, some red, some blue, depending on mass and stage. In the Milky Way, famous examples include Betelgeuse, a red supergiant in Orion, nearing the end of its life, and Rigel, a blue supergiant. When their cores can no longer sustain fusion, these massive stars die in titanic explosions, supernova, blasting their guts of heavy elements into space. Each supernova is like a brief, tragic fireworks show, outshining whole star clusters for weeks. Our galaxy has witnessed countless such explosions over its lifespan. They are part of its ecosystem. The remnants of these explosions, expanding clouds of gas like the Crab Nebula or Veil Nebula, lace the galaxy, adding to the diffuse background of matter that will one day form new stars. And what remains of the star itself can be a neutron star or a black hole, ultra-dense cinders of stellar cores that often quietly linger in the galaxy's disk or halo. Meanwhile, low-mass stars, far more common, especially faint red dwarfs that make up perhaps the majority of stars by number, live incredibly long, slow lives, longer than the current age of the universe in many cases. These red dwarfs form in the disk as well, and will burn their fuel so gradually they might outlast the galaxy's current form. These unobtrusive stars form the quiet backbone of the Milky Way's stellar population, too dim individually to notice, but collectively contributing significant mass. Stellar evolution in the Milky Way is a cycle. New stars form from gas enriched by older stars, live their lives, and then return material to the galaxy when they die. This cycle gradually changes the content of the galaxy. Early generations had almost no elements like carbon, oxygen, iron. Those were forged in stars and supernovae. Later generations, like the Sun, were born from clouds already seeded with these elements. Thus, our Sun contains about 2% of its mass in elements heavier than helium. Small, but enough to allow the formation of rocky planets like Earth. Without countless star lives and deaths before it, the Sun would have had no planets, or at least no solid ones, and we would not exist. The Milky Way's star population is thus intimately linked to everything around us, including life. The galaxy also sorts its stars by location. In the halo, we find primarily those old population 2 stars, with very low metallicity, a sign they formed when heavy elements were scarce. Many might be remnants of smaller galaxies the Milky Way gobbled up long ago. We'll get to that in galactic cannibalism. These halo stars often have orbits that plunge in and out of the disk at steep angles or swing far out, not the orderly carousel orbits of the disk stars. In the bulge, stars are again old on average, but slightly more enriched than the halo, and their orbits are randomly oriented, creating a spherical distribution. Some bulge stars may have formed in early mergers or in early starbursts in the young Milky Way. In the thin disk, we have stars spanning a range of ages, from newborns just a few million years old in spiral arms, to intermediate 5 billion-year-old stars like the Sun, to older disk stars, maybe 8 to 10 billion years old. The thin disk tends to host stars with higher metallicities, meaning each generation has incorporated more of those heavy elements. The thick disk stars are older, maybe 10 to 12 billion years, and have lower heavy element content. They might be the remnants of the early disk formed shortly after the halo, possibly created or heated during an ancient merger event that puffed up the disk. The Milky Way is essentially a stellar family tree. At its base are the ancient ones, the halo stars and globular clusters that can be over 12 billion years old, tracing back to the galaxy's youth. Then come the thick disk stars, slightly younger. Then the majority of the thin disk stars like our Sun, younger still. And at the tips of the branches, constantly budding, are the new stars being born today. The galaxy's current star formation rate is a few solar masses per year, meaning on average, a few new stars, some massive, many small, spark into existence each year across the entire galaxy. In regions like the Carina Nebula or the Sagittarius Arm, one can witness these newborns emerging and lighting up their surroundings. Interestingly, there's a chemistry to this evolution. The Milky Way's stars have gradually changed the composition of the galaxy's gas. Early supernovae seeded space with iron and magnesium. Dying red giants puffed out carbon and nitrogen. Neutron star collisions, rare but dramatic, may have forged gold and platinum and flung them into space. Over billions of years, the galaxy's gas has become a richer chemical stew, enabling new types of objects, like planetary systems with solid planets. Astronomers sometimes call this process chemical evolution, and they track it by measuring the spectra of stars, reading the barcode of elements present. In doing so, they can identify stars that share a common origin or era. For example, one might find a group of stars spread through the halo that all have a particular scarcity of iron but excess oxygen, clues that they might have come from the same long-gone dwarf galaxy that had its own unique chemical history. Stellar evolution also drives cosmic timekeeping. The color and brightness of stars across the galaxy tell us the epochs of formation. The presence of massive blue stars indicates ongoing or recent star formation, since those don't live long. The presence of many red giants indicates an older population. In the Milky Way, we see both. The arms are lit with blue stars, the bulge with red giants. We are living in a galaxy that is still actively forming stars, though not as furiously as it once did in its youth. Perhaps our Milky Way in its past had starburst periods when it churned out stars at a much higher rate, maybe triggered by mergers. Now it's in a more quiescent middle age, creating stars steadily but more slowly. However, middle age does not mean inactivity. Right now, as you listen, somewhere in the Milky Way, a star is exploding in a supernova, ending its life. Somewhere else, a cool cloud is fragmenting, and the spark of a new star is catching fire. A sun-like star might be quietly swelling into a red giant and engulfing any close planets. A binary pair of stars might be exchanging mass in a delicate gravitational dance, one siphoning from the other, perhaps to eventually trigger a nova eruption. The galaxy is alive with stellar happenings at every moment, a grand fireworks show in extreme slow motion. Each star also carries within it the memory of the galaxy's evolution. By studying them, scientists piece together how the Milky Way grew. For instance, they found some stars in the halo moving backward relative to the general rotation, evidence of an ancient collision that brought in stars on different orbits. They found that the thick disk has distinct chemistry, suggesting a turbulent formation, possibly a massive merger about 10 billion years ago that heated the early thin disk. Thus, the stellar populations and their properties are like pages in a history book. We live among these stars, unaware in daily life of their grand narratives. But if you step back, you can see that the Milky Way's stellar population is a complex tapestry, with threads of different ages and origins woven together by gravity. Ultimately, stellar evolution in the Milky Way is a story of continuity and renewal. Stars are born from the ashes of their ancestors and return material to keep the cycle going. It's poignant to think that in the future, long after we're gone, the atoms that currently make up Earth and our bodies might one day be blown into space by the sun's distant red giant phase, becoming part of a nebula, perhaps to be incorporated into new stars or planets. We are a part of this cosmic recycling. Our galaxy is not a static collection of eternal lights. It is a dynamic, evolving ecosystem of stars. As we leave the stellar garden, marvel at its variety, the hot, young stars shining like blue-white fireworks, the stately middle-aged stars like our sun nurturing planets, the elderly red stars casting a gentle glow, the ghosts of stars, white dwarfs, neutron stars, black holes, remnants that whisper of lives that came before. The Milky Way contains all of these in vast numbers. It's a stellar society spanning all stages of existence. With an appreciation for the lives of stars, we proceed to consider the material that both creates and is created by those stars, the gas and dust that fill the spaces between stars, the substance from which new worlds emerge and into which old ones dissolve. Gas and dust. Between the stars of the Milky Way lies the interstellar medium, a diffuse mixture of gas and dust that is the bloodstream of the galaxy. Though the night sky might look like mostly empty space with isolated stars, in truth, the galaxy is filled with this very thin matter. Gas and dust weave silently through the Milky Way's disk, concentrating in some places and dispersing in others, fueling starbirth and absorbing starlight. This is the galactic ecology's raw material, the substance that makes new stars and planets possible. It is also the main obstacle to our view, painting dark brushstrokes across the glowing canvas of the Milky Way when seen in visible light. What is this gas? Mostly hydrogen, the simplest and most abundant element, with a seasoning of helium and traces of heavier elements. In some regions, it's hot and ionized, in others cool and molecular, spread thinly on average, just a few atoms per cubic centimeter in typical regions, far emptier than any vacuum we can create on Earth. It nonetheless adds up across the vast reaches of space. Gas constitutes a significant fraction of the galaxy's normal matter. If you could gather all the gas in the Milky Way, it would equal billions of suns in mass. And the dust? Tiny solid grains, submicroscopic, composed of elements like carbon, silicon, oxygen, iron, the ash of stars, forged in supernovae, or the winds of red giants. Each dust mote is perhaps like a fine soot or sand grain, often coated with ices or organic molecules in cold clouds. Dust might only make up 1% of the mass of the interstellar medium, but its impact is outsized. It is extremely effective at blocking and scattering light. It's the dust that creates those prominent dark rifts that cleave the Milky Way's band in the sky, giant dust clouds obscuring the stars behind them. To our eyes, those regions look like cosmic voids, but truly, they are filled with material, just not luminous, invisible light. In fact, those dark clouds often harbor the conditions for future star formation, hiding embryonic stars in their lightless embrace. Gas and dust often gather together. In the spiral arms, as density waves pass through, gas clouds get compressed. Picture vast clouds, tens of light years across, cold and quiet, primarily molecular hydrogen, with dust sprinkled in. These are the giant molecular clouds, the cradles of stars. One such cloud in the constellation Orion is visible to us as a faint, hazy patch, the Orion Nebula, where young stars are lighting up the gas. Other clouds are entirely dark, detectable only by the way they block background starlight or via radio emissions from molecules inside them, like carbon monoxide, which astronomers use as a tracer. These clouds can contain the mass of thousands or even hundreds of thousands of suns. Within them, dust shields the interior from harsh starlight, allowing molecules to form and temperatures to drop to just a few tens of degrees above absolute zero. In these frigid, dense pockets, gravity can overcome pressure and cause parts of the cloud to collapse, initiating star formation. Thus, gas and dust are the maternity wards of the galaxy. As new stars ignite inside a cloud, their radiation and stellar winds begin to disperse and sculpt the gas. They create glowing H2 regions, zones of ionized hydrogen that shine with a reddish-pink hue in photographs. These nebulae are essentially the cloud's announcement that stars have been born. The Trifid Nebula, the Lagoon Nebula, the Eagle Nebula, with its famous pillars of creation. These are all examples within our Milky Way of gas, lit up by newborn star clusters, captured in stunning detail by our telescopes. In these images, we often see towers and pillars of denser gas resisting the onslaught of radiation, sometimes harboring yet more protostars at their tips. The interplay of starlight and cloud creates beautiful structures, like cosmic sculpture parks carved by ultraviolet light. Eventually, the young star's energy blows away the remnants of the parent cloud, dispersing the gas and dust back into the general interstellar medium. There, the material may drift until another spiral arm or compression gathers it again. Not all gas is in cold clouds. There is also warm interstellar gas spread throughout the disk, partially ionized by ultraviolet starlight, creating a very tenuous plasma that fills much of the volume. There are hot bubbles too, cavities blown by supernova explosions where gas has been shock-heated to millions of degrees and is expanding outward. The galaxy's disk likely has a patchwork of these phases: cold, dense clouds, warm, diffuse gas, and hot, ionized bubbles. They coexist like different climates across the lands of the Milky Way. Gas and dust serve as a record of events. When we find certain heavy elements or isotopes in the gas, we know a supernova contributed them. When we detect complex organic molecules in a cold cloud, we realize chemistry is happening in space. Molecules like formaldehyde, alcohols, even simple sugars and amino acid precursors have been identified in interstellar clouds. It's astonishing. In the emptiness of space, tiny dust grains can catalyze the formation of complex molecules so that clouds many light years away hold some of the same chemical ingredients that on Earth lead to life. This interstellar chemistry is a rich field. One could say the galaxy has its own chemistry lab, continuously running experiments in the cold and dark, forging new molecules that one day might be incorporated into planets or even life forms. We owe a lot to dust. It facilitated the cooling of clouds to form stars, and later, in protoplanetary disks around new stars, dust grains clumped to form planetesimals and eventually planets. But dust also obscured our view. For centuries, it hid the true extent of the Milky Way. Early star counters like William Herschel in the 18th century tried to gauge the galaxy's size by counting stars in different directions, not realizing that dense dust clouds blocked the light in some directions. This led to an underestimated size and a mistaken idea that the Sun might be near the center of the galaxy. Only later did astronomers like Harlow Shapley realize, by studying globular clusters, which lie outside the dust of the disk, that the center of the Milky Way was far away in Sagittarius, and that our galaxy was much larger than previously thought. The dust had fooled us by dimming distant stars. Today, we have overcome dust's veil by observing at different wavelengths. Infrared light can penetrate dust much more effectively, allowing telescopes like Spitzer and now the James Webb Space Telescope to peer into dusty regions and see stars being born. Radio waves from certain atoms or molecules, like the 21 centimeter line of neutral hydrogen or rotational lines of CO, allow us to map the gas distribution throughout the galaxy, dust or no dust. These techniques revealed the spiral arm structure by tracing the gas that makes them up, even when those arms lie on the far side of the galaxy, hidden behind intervening dust. In fact, one of the first maps of the Milky Way's spiral structure came from radio observations of hydrogen gas. The dust, which once hid our galaxy's structure like a veil, has had that veil lifted by modern astronomy. Gas also connects the Milky Way to its environment. The outer reaches of the galaxy's halo contain very diffuse gas clouds, some of which are left over from interactions with satellite galaxies. A famous example is the Magellanic Stream, a long ribbon of gas trailing behind the large and small Magellanic Clouds, two of our satellite galaxies, as they orbit the Milky Way. This stream, tens of degrees across the sky, is essentially those galaxies' gas being stripped and drawn toward our own. Eventually, that gas may rain down onto the Milky Way's disk, galactic rain, and fuel future star formation. There are also high-velocity clouds, mysterious giant blobs of gas moving quickly relative to the rest of the galaxy, possibly remnants of past encounters, or cold gas from intergalactic space captured by our halo's gravity. Within the disk, gas moves and flows. As the galaxy rotates, differential rotation can shear giant clouds, draw them into spiral patterns. When supernovae explode, they can send out shock waves that compress nearby gas, potentially triggering new star formation in surrounding clouds, a process akin to a chain reaction of starbirth. Alternatively, multiple supernovae can combine their shock power to punch holes in the disk and blow gas out into the halo, creating galactic fountains of hot gas that eventually cool and fall back. In this way, gas cycles not just in and out of stars, but also between disk and halo in a circulation often called the Galactic Fountain. The dust, for its part, sometimes shows us beautiful phenomena. In the densest clouds, dust is so opaque that optical light can't get through. But if there are bright stars nearby, dust can reflect their light, creating reflection nebula. Ethereal blue glows near young stars. Blue because dust scatters blue light more easily, similar to why our daytime sky is blue. We see this in the Pleiades star cluster. The hot young stars are surrounded by a blue sheen from dust reflecting their light. Dust also causes distant stars to redden. Since blue light is scattered out, more red makes it through, a clue to its presence. As we float conceptually through a spiral arm, we would pass through regions of dense gas and dust where stars are forming, then into clearer spaces where older stars roam, and perhaps past the bubbles of prior supernova. It would be like driving alternately through foggy patches and clear skies on a country road at night, sometimes seeing only nearby things, other times seeing far. In a poetic sense, gas and dust are the breath of the galaxy. They move, they flow, they condense and dissipate as the Milky Way lives and evolves. They are invisible to our unaided eyes, yet they make their presence known through the twinkle of starlight. Stars twinkle partly due to Earth's atmosphere, but interstellar gas can also cause scintillation or dimming over vast distances, and through the absorption of light, carving dark river-like shapes in the Milky Way's band in the sky that inspired so many myths. One such dark shape, visible from Earth's southern hemisphere, is the Coal Sack Nebula, a prominent dark cloud in the Crux constellation, which appears as a big hole in the Milky Way's starband. Australian Aboriginal peoples saw such dark clouds as significant shapes as well. Some saw an emu outlined in the darkness against the Milky Way. These cultural interpretations were early acknowledgements of interstellar dust's visual effect, long before science understood them as clouds of dust. Consider also that the interstellar medium whispers with electromagnetic radiation. The 21-centimeter radio whisper of neutral hydrogen permeates the galaxy. If you tune a radio telescope to that frequency, you can literally detect the diffuse hydrogen gas between the stars. It's a very faint signal, but it's everywhere, a kind of secret language that atoms are speaking across the galaxy. Using it, astronomers map spiral arms and measure rotation. As we appreciate gas and dust, we should also note the role of galactic magnetic fields. Though hard to imagine, our Milky Way has a magnetic field threading through its gas, a bit like the Earth has a field, though far weaker, on the order of microgauss. These magnetic lines influence the motion of charged particles and the alignment of dust grains. Sometimes we can detect the polarization of starlight caused by dust grains aligning with magnetic fields, giving us a glimpse of this invisible component. It's as if the galaxy has an unseen lattice that can gently steer particles, another layer of complexity in the interstellar medium. These fields might help channel cosmic rays, high-speed charged particles, through the galaxy and possibly affect star formation by providing pressure in gas clouds. In sum, gas and dust are the Milky Way's substance of creation and change. They form the clouds that birth stars, carry the products of stellar death, obscure and redden the light, and bridge the space between stars with a tenuous presence. They are, in a way, the memory of the galaxy's past and the womb of its future. Every star that will ever shine in the Milky Way will come from the gas and dust that float among the current stars, and every star that dies will return much of its substance to that reservoir. It's a cycle of cosmic reincarnation. Now, having explored the diffuse media that bind the stars, let us journey to the center of the Milky Way, a place both wondrous and forbidding, where the density of stars soars and an enigmatic darkness sits enthroned at the core. The Galactic Center. Toward the constellation of Sagittarius, hidden behind swathes of dust, lies the Milky Way's mysterious capital, the Galactic Center. This is the central hub of our galaxy, a place of extremes and secrets. If the Milky Way is a city of stars, then the Galactic Center is downtown, vibrant, crowded, and always bustling, yet also home to the darkest, most enigmatic figure in our galaxy's story, a supermassive black hole. Approaching the Galactic Center, in our mind's eye, since physically it's 26,000 light-years away, the first thing we'd notice is the sheer density of stars increasing. In the inner few hundred light-years, stars are packed like a glittering swarm. Within just 1 light-year of the center, it's estimated there are millions of stars. Compare that to our neighborhood around the Sun, where the nearest star is over 4 light-years away. In the Galactic Center, stars can be only weeks of light travel apart from each other. The night sky from a planet in that region would be dazzling beyond imagination. Darkness scarcely exists, as you'd be surrounded by countless brilliant stars in every direction. Most of these central stars are older, redder stars, members of the bulge population. But intriguingly, intermingled among them are some blue stars, surprisingly young stars found very close to the black hole. How they got there is an active question in research. Possibly they formed from gas, funneled to the center, or maybe they were brought in as part of star clusters that migrated inward. Regardless, it means the Galactic Center is not just a graveyard of old stars. New life can spark, even in this hectic environment. Now, at the very core, at the precise center of the Milky Way's rotation, resides Sagittarius A, pronounced Sagittarius A star, the supermassive black hole of about 4 million times the mass of our Sun. It's currently quiet, a sleeping giant, but it profoundly affects its neighborhood. Stars closest to it are whipping around at speeds up to a few % of the speed of light, caught in its intense gravitational grip. We know this because astronomers have observed these stars, the so-called S-stars, over decades, tracking their orbits using infrared telescopes that can see through the dust. One star, named S2, orbits the black hole on a highly elliptical path that takes it within just 17 light hours of the black hole, about 120 AU, only a few times farther than Neptune is from our Sun, at its closest. At that point, S2's speed is an astonishing 3% of light speed, 5,000 km/h. It completes one orbit every 16 years. Watching these stars swing around an unseen point showed conclusively that an extremely massive, compact object, a black hole, must lie at the center. This earned scientists like Andrea Ghez and Reinhard Genzel Nobel Prizes, as it provided some of the best evidence for the existence of supermassive black holes. Standing near the black hole, though one cannot truly stand there, one would witness bizarre effects. The gravitational field is so strong that light from stars behind it gets bent and distorted. Time itself runs a bit slower, closer to the black hole compared to farther away, a result of general relativity. Yet, Sagittarius A is relatively gentle as far as black holes go, because it's in a quiet phase, not actively devouring large amounts of matter right now. If it were active, we would see a bright beacon of high-energy radiation, X-rays, etc., and perhaps jets of particles shooting out from the poles, as seen in quasars. Instead, our black hole dines modestly. Occasional small gas clouds or asteroids might wander too close and get swallowed, producing flares. Indeed, astronomers have seen occasional X-ray and infrared flares from Sagittarius A, likely from small chunks of matter heating up just before disappearing across the event horizon, the point of no return of the black hole. The environment around the black hole is not empty. There's a swirling disk of gas and dust, though currently thin, known as an accretion flow. There are also clumps of matter like the intriguing object called G2, initially thought to be a gas cloud on a collision course with the black hole in 2014, but which survived the encounter and might conceal a star at its core. Additionally, the central region houses some unique astrophysical objects. Clusters of massive stars, the Arches and Quintuplet clusters, perhaps formed in starbursts a few million years ago, and many pulsars and X-ray binaries likely exist there, though they are hard to detect due to crowding and interstellar absorption. Moving out a bit, say within the inner few hundred light-years, what we call the central molecular zone, the gas density increases. There are massive molecular clouds swirling around the center, some arranged in a ring or torus about 2 to 5 light-years from the black hole, often called the circumnuclear disk. These clouds are subject to strong tidal forces and sometimes fall inward, feeding the black hole in dribs and drabs. The region also has unusually strong magnetic fields and cosmic ray activity. It's as if the vicinity of the galactic center is a different world compared to the quieter suburbs where we live. One of the most remarkable large-scale features tied to the galactic center are the Fermi bubbles. In 2010, scientists using the Fermi Gamma Ray Space Telescope discovered 2 enormous lobes of high-energy emission extending above and below the plane of the galaxy, centered on the core. Each bubble is about 25,000 light-years tall. They rise like twin balloons or mushroom clouds from either side of the nucleus. These bubbles shine in gamma rays and X-rays, indicating they are filled with extremely hot gas and cosmic ray particles. They likely attest to an energetic event in the Milky Way's center a few million years ago, perhaps a period when Sagittarius A devoured a batch of matter and blew out a pair of jets, or a burst of star formation and supernovae in the core that drove a galactic wind. Today, the bubbles are fading, but still glowing, ghostly echoes of that past activity. If we had gamma-ray vision, the sky would have two huge ovoid shapes north and south, dwarfing the full moon. These show that while the galactic center is relatively calm now, it hasn't always been so. It has had its quasar-like moments or burps. From a human standpoint, if you could travel to the galactic center, ignoring lethal radiation and such, the sight would be awe-inspiring. Stars everywhere, a gentle reddish hue from myriad red giants, intense orbital dynamics, and at the very heart, a featureless dark void marking the black hole, perhaps detectable not by sight, but by the motion of stars, and by a faint glow of doomed matter around it. Actually, in 2022, the Event Horizon Telescope collaboration gave us our first image of Sagittarius A, a ring of radio emission around a dark center, the black hole's shadow, a bit like the famous photo of the M87 galaxy's black hole, but much smaller in angular size. It confirmed the presence of the expected event horizon silhouette, further proof of the behemoth lurking there. Culturally and historically, the galactic center was unknown to us until radio astronomy. In visible light, that direction is obscured by thick dust clouds, like the Great Rift. We only realized something special lay there when in the 1950s, strong radio emissions, Sagittarius A region, were detected. Over time, multi-wavelength observations peeled away the layers of obscuration. Now we know Sagittarius A not as just a radio source, but as a black hole. If Earth's night sky were not obscured by dust towards Sagittarius, who knows? Perhaps ancient astronomers would have built temples or stories around a bright object there. But instead, it was hidden, maintaining its mystery until modern times. The galactic center is also rich in molecules. The clouds in this zone have produced some of the most complex molecules detected in space, likely due to the higher density and interesting energy sources. For example, molecules like acetone, methanol, even ethyl formate, a molecule that smells like rum, interestingly, have been found in Sagittarius B2, a giant molecular cloud near the center. It's a chemist's treasure trove. It's fascinating to think that while we orbit calmly far away, the center is such a frenetic place, but its influence reaches us. The mass of the central black hole is negligible for the galaxy's overall gravity. The dark matter and stars dominate on large scales. But in aggregate, the central mass concentration anchors the rotation and influences the bar structure that extends across the inner galaxy, which in turn helps shape the spiral arms. It's all connected. At times, I picture the Milky Way's center as a kind of cosmic hearth, a fireplace at the center of a great hall. It may burn low or fiercely, but it's the focus around which the structure of the house is arranged. Right now, our hearth is glowing quietly, but who knows in a few million years or in the past, it might have flared, sending sparks, radiation, winds across the galaxy's inner regions. So as we think of the galactic center, we think of paradox. It is both the brightest concentration of stars and home to the darkest of objects. It's a place where time and space are warped by extreme gravity, yet from which our galaxy's spiral structure gracefully unfolds outward. It is central and crucial, yet largely hidden from our direct view. To feel it, we must rely on instruments and imagination. Let's pause a moment and imagine ourselves floating a few light years from Sagittarius A, shielded safely, looking outward. The sky is ablaze with the glow of 10 million stars. Perhaps we see the spiral arms from the inside, radiant streams extending outward. Above and below, beyond the disk, faint glows hint at the Fermi bubbles. The black hole behind us is invisible, save for the swirl of hot gas around it, making a sort of dim halo. We feel the space-time vibrating with activity, stars slingshotting by, X-ray flashes from small matter falling in, the hum of dense star clusters. It's both serene in its grandeur and terrifying in its intensity. In the silence of space, this chaos is oddly mute, but one can sense the energies at play. Having dared to visit the heart of the Milky Way, let us journey back outward a bit to consider something the galactic center helped reveal: the rotation curve of our galaxy and what that means, bridging back to our earlier thoughts on the invisible architecture. The rotation curve. One of the most illuminating ways to understand a galaxy is to study how it rotates. Imagine watching the Milky Way spin over time, sped up enormously, of course. How do the stars and gas move as a function of distance from the center? The graph of orbital speed versus radius is called the rotation curve. For the Milky Way, as with many other galaxies, the rotation curve holds a surprising story that forever changed our understanding of the cosmos. In a simple world, you might expect the inner parts of the galaxy to rotate fast and the outer parts to rotate slower, much like planets in the solar system, where Mercury zips around fast and distant Neptune moves more slowly. If most of the mass were concentrated in the center, like the Sun in our solar system, that's exactly what you'd see. Speeds would drop off with distance. However, when astronomers measured the motion of gas and stars at various radii in the Milky Way, they found something astonishing. Beyond a certain point, the rotation speeds did not drop off. They stayed roughly constant or flat, and even out to large radii remained high. In the inner region, inside roughly a few thousand light years, speeds increase with radius as one moves out from the central bulge. This is normal, because initially, you're still adding more enclosed mass as you go outward, so gravity grows. But beyond the inner bulge disk, instead of peaking and then declining, the curve plateaued. Stars and gas far from the core, tens of thousands of light years out, were orbiting at roughly 200 to 240 kilometers, nearly as fast as those much closer in. This flat rotation curve was one of the key pieces of evidence that led to the concept of dark matter, which we discussed in the invisible architecture. It told us that the mass of the Milky Way keeps increasing with distance far beyond the visible disk. There must be a lot of unseen mass out there providing the gravitational pull to keep those outer stars moving fast without flying away. Without that extra gravity, the outer stars and gas clouds, moving as fast as they do, would escape the galaxy's grip. The rotation curve basically mapped out the presence of the dark matter halo. As you go out, you keep encountering more mass that's not shining. However, even with this general understanding, scientists continue to refine the Milky Way's rotation curve with better data. It's not a perfectly flat line. It has subtle bumps and wiggles. For instance, around the Sun's orbit, 27,000 pounds-li, the speed is around 220 kilometers. Further out, it might gently rise or fall by small amounts. Recent precise measurements from Gaia and other surveys indicated the curve might even decline slightly in the far outer disk, suggesting maybe less dark matter in the outskirts than some models predicted, though the data are tricky. Still, broadly, it remains far higher at large radii than a visible matter-only galaxy would allow. One can think of the rotation curve as a kind of diagnostic of the galaxy's mass distribution. In the Milky Way, it tells us that the luminous parts, stars, gas, are only the tip of the iceberg of mass. The dark halo's distribution is such that even at distances where the starlight fades, mass is still accumulating. Historically, measuring the Milky Way's rotation curve had challenges because we're inside the disk. Astronomers used a clever method, observing the 21 centimeter radio emissions of hydrogen gas in different directions. In certain directions along the inner galaxy, they could measure Doppler shifts that indicated how fast gas was orbiting. By mapping the velocities as a function of galactic longitude and using geometry, they inferred the rotation speeds at different radii. External galaxies provided additional confidence. Vera Rubin's pioneering work in the 1970s on spiral galaxies showed flat rotation curves were common, not just an oddity of the Milky Way. The rotation curve is often plotted with orbital speed on the vertical axis and distance from center on the horizontal. For the Milky Way, it rises from 0 at the very center, though motions there are more random due to the bulge. Peaks around maybe 200 to 240 km in the inner disk, and then stays around that value out to as far as we can measure, maybe 60,000 light-years or more. If the galaxy's mass ended around the visible edge, half 50,000 Panspermie radius, the curve would start dropping, but it doesn't significantly, indicating the halo extends much further. Think of a carousel again, but imagine invisible weights are hidden under the floor, extending way out beyond the visible platform. The horses near the edge keep going fast because those hidden weights provide the gravitational pull. There's also something poetic here. The stars in the Milky Way are essentially flying in enormous circles, guided by gravity's hand. We don't feel this motion sitting here on Earth, but it's real and enormous in scale. Each star's orbit is a balance. Its motion is trying to fling it away, but gravity pulls it in. At the radius of the Sun, that balance has us moving at roughly 500,000 miles per hour around the center. At the edge of the disk, a star might still be moving at 400,000 km/s. The galaxy's rotation is the reason the Milky Way has maintained a disk shape. If it rotated much slower, gravity would collapse more material inward. If it were faster, perhaps the outer parts would break away. Rotation also ties intimately with the spiral structure. The arms are not material arms that rotate like a solid object. They are patterns through which stars and gas move. The differential rotation, inner parts rotating faster in terms of orbital period than outer parts, means any material arm would wind up tighter and tighter. So the prevailing idea is that spiral arms are a kind of density wave that rotates at its own pattern speed, and stars enter and leave it, like cars moving through a traffic jam region. The rotation curve plays a role in where these pattern resonances occur. It's amazing that from the simple question, how do stars move in the galaxy, we unveiled something as profound as dark matter. The rotation curve is like the galaxy's heartbeat chart. For humans, a heart ECG can indicate health or problems. For the galaxy, the rotation curve indicates a hidden vital component. Let's reflect a moment on what it would feel like if we could sense this rotation personally. Right now, sitting or standing, you might feel at rest, yet you are on a planet spinning on its axis, orbiting the Sun, and also careening around the galactic center. The motion around the galaxy is by far the fastest of these at any given moment, since 220 km dwarfs Earth's orbital, 30 km or rotation, still 0.5 km at equator. So we are all passengers on a starship called the Solar System, cruising through the Milky Way at tremendous speed. The stars we see near us share roughly the same orbital motion. They're our fellow travelers. More distant stars, if you track them long enough, show up with different velocities due to perspective and their position. Gaia's measurements of star motions let us see the kinematics in exquisite detail. How some stars stream together in groups, perhaps remnants of disrupted clusters or past mergers. How the disk might have subtle waves or corrugations, possibly from the influence of satellite galaxies, like the Sagittarius Dwarf or LMC. The rotation curve, being flat, implies the presence of that dark halo we spoke of, which itself is a major character in our story. Without dark matter's gravitational support, the Milky Way might not have formed as it did, and the rotation would be quite different. Some alternate theories have been proposed, like modified gravity theories, to explain flat rotation without dark matter, but none have matched all evidence as well as the dark matter halo model for our galaxy and others. From a narrative perspective, the rotation curve is like reading the galaxy's diary in a language of motion. It told us that the Milky Way has more to it than meets the eye, an insight somewhat akin to reading someone's calm outward expression, but sensing an underlying strong heartbeat. It's the clue that led us down the path of acknowledging the invisible architecture in quantitative detail. As we continue outward or onward in our journey, The rotation curve concept will segue nicely into discussing the dark matter halo specifically, since it's responsible for that shape of the curve. We have essentially set the stage. The galaxy rotates in such a way that reveals the dark matter. Now we'll explore that halo in more depth, albeit in a poetic tone, since dark matter is inherently mysterious. So, with stars swirling around us in a gravitational dance and speeds that defy the luminous mass, we prepare to meet the dark halo face to face, or rather, face to something we cannot see, but know is there by its embrace. Dark matter halo. Enveloping the Milky Way like a cocoon is the dark matter halo, a vast and enigmatic component that extends well beyond the visible galaxy. We've already felt its gravitational influence in the flat rotation curve and the invisible architecture. Now let's visualize this halo and contemplate its nature and significance, as if meeting the ghost in our galactic home. Imagine a sphere centered on the Milky Way, perhaps as large as 1,000,000 light-years across, nearly half the distance to the Andromeda galaxy. Within this sphere, sprinkled very lightly, are particles of dark matter, something we do not yet understand fully, be it an exotic particle or something stranger, but which has mass and thus gravity. These dark matter particles neither emit nor absorb light. They pass through ordinary matter, almost as if it wasn't there, interacting mainly via gravity. They are elusive. Billions might be passing through you right now without a trace. Yet, their cumulative effect around the galaxy is immense. They account for about 90% of the Milky Way's total mass. The dark matter halo likely formed early, before the galaxy's stars were born. In the young universe, slight density variations caused some regions to collapse into clumps dominated by dark matter. These were the seeds of galaxies. One of those seeds became the halo of the Milky Way, pulling in gas which then formed stars and the disk within. Over time, smaller halos merged, assembling into the larger halo we have now, dragging their luminous contents, stars, gas, with them. Even today, the halo might have substructure, clumps or subhalos of dark matter, perhaps hosting small satellite galaxies or just invisible on their own. What is the shape of our dark halo? We often imagine it spherical, but it could be a slightly squashed sphere, triaxial, or oblate. Studies of stellar streams, remnants of torn-apart dwarf galaxies, serve as tracers, like throwing paint on an invisible object to see its outline. These studies suggest the halo might be a bit elongated or lopsided, especially given a big lump like the Large Magellanic Cloud may even distort it a bit. But roughly, it's a huge roundish cloud of mass around the Milky Way. In that halo, aside from dark matter, there's a tiny population of visible things, the halo stars and globular clusters we discussed, and the satellite galaxies orbiting within it. They are like fireflies around an elephant, bright but insignificant in mass compared to the dark matter bulk. If you could view the Milky Way from afar in the dark matter spectrum, whatever that might be, you'd probably see a smooth glow, if dark matter glowed, about 10 times the diameter of the visible spiral, maybe tapering off gradually at the edges, with slight ripples where subhalos might reside. The visible galaxy would lie at the center as a bright jewel in a glass paperweight. This halo is the gravitational cradle of our galaxy. It keeps everything bound together. When our galaxy engages in cosmic interactions, it is the dark matter halo that largely dictates the outcome because it's the dominant mass. For instance, if the Milky Way passes near another galaxy, it's the halos that feel each other first, tugging gravitationally like invisible giants meeting before the visible galaxies ever touch. Dark matter's presence also shields and shepherds the galaxy's content. It provides an additional gravitational well, such that even as the galaxy rotates rapidly, the stars remain secure in orbit. Without the halo, a fast-rotating disk might fly apart. The halo's gravity holds the disk intact, much like an egg's invisible gravitational field might hold a spinning yolk in place. if one can imagine such a thing. What is especially intriguing is that we know dark matter exists through effects like these, but we don't know what it is. It's one of the greatest scientific mysteries of our time. It could be a type of particle left over from the Big Bang that interacts only via gravity and perhaps the weak nuclear force. Many experiments on Earth are trying to directly detect a dark matter particle in underground detectors, so far without confirmed success. It could even be something more exotic, primordial black holes, or something not predicted yet. But in the grand narrative, in the Milky Way's tale, dark matter is a silent character who never speaks, never reveals its face, yet whose actions shape everything. The halo does interact gravitationally with visible matter in ways beyond just holding it. It likely plays a role in how material flows into the galaxy. For instance, fresh gas from intergalactic space might be attracted by the halo's gravity, then slowed or shock-heated upon entry. It may accumulate in the halo as hot gas. Some theories say there's a hot, circumgalactic medium, a very low-density, million-degree gas pervading the halo, detected via X-ray and UV absorption lines. That gas can slowly cool and rain onto the disk, fueling new star formation. So the halo could be seen as the galaxy's reservoir, catching incoming material in a gravitational net. The halo also can capture or destroy other small halos. When a dwarf galaxy ventures close, if the tidal forces from the Milky Way's halo exceed the dwarf's self-gravity, the dwarf gets torn apart. Its stars become streams. Its dark matter likely just assimilates into the Milky Way's halo. Over cosmic time, the halo has probably grown by eating many smaller ones, an unseen feast leaving behind star stream crumbs as the only visible evidence. It's mind-bending to consider that most of the Milky Way's mass lies in this unseen halo. To draw a metaphor, imagine meeting a person and discovering that 9/10 of their body is invisible, and you only see an arm, part of a face, and a foot perhaps. You'd realize you really don't know the full person at all. That's our situation with the galaxy. We see its stars and nebulae, the parts sticking out, but the bulk is hidden. And that is true for all galaxies, not just ours, hinting at something fundamental about the cosmos. For our narration, let's personalize the halo a bit. Think of it as a gentle giant surrounding the bright hubbub of stars. It's mostly quiet, interacting by gravity's pull. It doesn't shimmer or shine, but it has enormous influence. If the disk of the Milky Way is like the visible dance of a music box ballerina, the halo is the unseen mechanism that provides the structure and momentum for the dance. There's also a sense of melancholy with dark matter. It's so important, yet it doesn't partake in the flashy parts of cosmic evolution. No light, no chemistry, no forming of planets. As far as we know, dark matter cannot clump to small scales because it doesn't radiate energy, so it can't cool and collapse to form things like stars or planets. It stays in a large, diffuse halo. It's like a scaffold that builds a cathedral, but once the cathedral, stars, planets, is built, you take away the scaffold's visible role. Yet the scaffold was necessary. We might wonder, do dark matter particles pass through us? Yes, if they exist as particles. Earth is moving through the galaxy's halo, so presumably a wind of dark matter flows through at hundreds of km/s. They rarely, if ever, hit our atoms in a noticeable way, but experiments are trying to see a faint tap of a dark matter particle hitting a detector nucleus. From a philosophical standpoint, the dark matter halo reminds us that much of reality might be hidden from direct view. In the Milky Way, what you see is not all there is. One must infer, deduce, and feel the effects of the unseen. In life, too, sometimes what's important is not immediately visible. It's a nice parallel. Now, another feature of having a dark matter halo is that it extends the influence of the Milky Way far out. There's no clear edge to the galaxy because of the halo. It gradually peters out. This makes the concept of where the Milky Way ends fuzzy. Some define the edge where the escape velocity equals the rotational velocity, etc. But thanks to the halo, one could say our Milky Way has a radius on the order of 300,000 light-years or more, where the density of dark matter merges into the general background of space. The nearest big galaxy, Andromeda, has its own halo, and interestingly, these halos might already be touching or overlapping in the space between Milky Way and Andromeda, like two giant soap bubbles gently contacting. If so, then in some sense our local group, the group of galaxies including Milky Way, Andromeda, and some dwarfs, is one connected structure through the dark matter distribution. It's a lovely concept that even before the galaxies themselves collide, which they will in billions of years, their dark halos have met. In closing our consideration of the dark halo, let's envision drifting outwards from the bright disk into the realm of darkness. As the starlight fades behind us, we plunge into an almost empty vastness. But we're not alone. The gravitational pull is still with us, indicating mass all around like a subtle tension in space. Occasionally we might pass a lone globular cluster or a small satellite galaxy, little islands of light in the dark sea. But mostly, it's quiet and dark. If we could see the dark matter, maybe it would look like a faint mist or swirl around us. Perhaps it's clumpy. Maybe we pass through an invisible cloud that is a subhalo. We wouldn't know, except perhaps by a slight tug. The main Milky Way disk now is a small shining disk far behind, like a distant lighthouse. Yet the domain of our galaxy extends much farther, here in this dark realm. We realize that as we leave the visible behind, the Milky Way's influence has not ended. It extends its gravity out here in the silence. And interestingly, out here, we might find things like star streams and signs of galactic cannibalism, evidence of how the Milky Way grew. So now, let's follow one of those streams of stars, a tenuous bridge of lights crossing the dark halo, which tells the tale of galactic cannibalism, the ongoing process by which our galaxy has consumed others. Star streams and galactic cannibalism. In the Milky Way's halo, if you look closely, with the powerful eyes of missions like Gaia, you'll find stars arranged in long, arcing filaments, as if drawn out into lines by a cosmic comb. These are stellar streams, the remnants of small galaxies or star clusters that ventured too close to the Milky Way and were torn apart. They are the ghostly footprints of past galactic meals, evidence of what we call galactic cannibalism, the process by which our large galaxy grows by devouring smaller ones. Picture a smaller dwarf galaxy, perhaps millions or a billion stars, bound loosely together, orbiting the Milky Way. Over time, gravitational tidal forces stretch it. Stars from the dwarf begin to drift out, forming a stream, trailing and sometimes leading the core of the dwarf, like taffy being pulled apart. Eventually, the dwarf structure dissolves, leaving behind a stream of stars orbiting the Milky Way along what used to be the dwarf's path. These streams can wrap around the galaxy in huge loops. They're faint, but with precise measurements of star positions and motions, we can detect them as overdensities of similarly moving stars. One famous example, the Sagittarius stream, from the Sagittarius dwarf spheroidal galaxy, which has been in the process of merging with the Milky Way for billions of years. The core of this dwarf is still present, a dim, fuzzy galaxy on the opposite side of the galaxy from us, toward the constellation Sagittarius, hence the name. But it's being dismantled. Wraps of its stars have spread in a polar orbit around us. Indeed, part of that stream passes relatively near the Sun's position, though still tens of thousands of light years away. It forms a huge structure encircling the galactic halo. Imagine a gossamer ribbon of stars, too faint to see without telescopes, looping over the top of the Milky Way and around beneath. That's the Sagittarius stream. Another, the GD1 stream, thought to be from a globular cluster that was torn apart. Or the Palomar 5 stream, another shredded cluster leaving a thin stream behind. There are others like Orphan Chenab stream, poetically named because the progenitor is gone, an orphan, and the Helmi streams, discovered by an astronomer, Amina Helmi, which are remnants of a dwarf galaxy that merged early on. And then, one of the most significant events in the Milky Way's history has been deduced by studying the halo star's motions and chemistry, a collision about 8 to 11 billion years ago with a dwarf galaxy often called Gaia Enceladus, or the Gaia sausage. This oddly nicknamed object was a fairly large dwarf galaxy that smashed into the early Milky Way. Many of the halo stars and the halo's inner portions have orbits and compositions indicating they came from this event. The name sausage comes from a pattern in velocity space that looks like a sausage shape when plotted, identified in Gaia data. This merger is believed to have puffed up the Milky Way's thick disk and given it a lot of its halo. In a sense, we are partly a chimera. Our galaxy is partly built from the remains of that galaxy. After the collision, the stars of Gaia Enceladus were strewn into radial orbits, going out and back in, which is why in velocity space they have high radial motions but not much rotation, giving that sausage signature. That event likely also caused a burst of star formation and altered the structure of our young Milky Way. Galactic cannibalism may sound violent, and indeed on a cosmic scale, it is a sort of violence. But remember, stars are so far apart that when two galaxies merge, individual stars almost never collide. Rather, the system's gravitational fields merge. The smaller galaxies' stars simply find themselves gradually reassigned to orbit in the gravitational potential of the bigger galaxy, rather than their original small one. The violence is in the gravitational forces that rip the structure apart, and any gas in those galaxies can get compressed and create flashes of new stars, starbursts, or feed the central black hole, etc. Over time, the smaller galaxy is fully digested, its stars now just part of the halo or disk of the Milky Way, its distinct identity gone. Our Milky Way has probably consumed dozens of smaller galaxies over its lifetime. Some were long ago. Their stars are thoroughly mixed, and we only find hints by finding stars with unusual chemistry or orbits. Others are ongoing, Sagittarius, or recent, like Gaia Enceladus. 10 billion years is recent in a 13 billion year life. This process is common in the universe. Big galaxies like ours grew by hierarchical merging, assembling from smaller pieces. Even the Large Magellanic Cloud, LMC, that orbits us now is destined for this fate. The LMC and its smaller companion, the SMC, Small Magellanic Cloud, are falling toward the Milky Way. Within a few billion years, they might merge into us. Some models say the LMC will fall in sooner than Andromeda's arrival. When that happens, it will induce new star formation, perhaps create new streams, and add its stars, and even its own central black hole. The LMC likely has an intermediate mass black hole, which may merge with our central black hole eventually. This cannibalistic side of the Milky Way is a reminder that galaxies are not static islands. They are dynamic and continually evolving. For smaller galaxies in our vicinity, the Milky Way's gravity is a force of destiny. Over time, the Milky Way will incorporate many of them. It's almost like the mythology of Cronus devouring his children, except the Milky Way devours smaller siblings. But it's not malicious, it's just gravity doing its inexorable work. The stellar streams left behind have a serene beauty to them. I like to think of them as cosmic rivers in the galactic halo, or perhaps the fossil rivers of what once were independent galaxies. They also serve as signposts. For instance, the way a stream's path bends can tell us about the shape of the dark matter halo. The stream is essentially a test particle, feeling the gravitational field. One day, maybe we'll map dozens of streams and thereby map the dark matter distribution precisely. Also, some globular clusters might be immigrants from swallowed galaxies. Some clusters have different properties that suggest they originally lived in a dwarf galaxy that got merged. and the cluster got adopted by the Milky Way. From our vantage in the solar system, these events are subtle. The night sky doesn't obviously show a stellar stream to our naked eyes, except maybe one can argue that the Milky Way's own band had to be recognized as our galaxy, not a stream through it. That was another story from Shapley versus Curtis. But through telescopes, we can detect certain patterns. For example, the Sagittarius dwarf galaxy can actually be imaged as a faint concentration of stars, only discernible with telescopic surveys. And if you plot the positions of certain types of stars, like RR Lyrae variables or blue horizontal branch stars, which often reside in old populations, at large distances, you can see overdense bands corresponding to known streams. Galactic cannibalism will continue into the future. Eventually, the Milky Way itself will be devoured, or rather, merged, when we collide with Andromeda. But by then, in that merged entity, all the smaller galaxies we had left, maybe the Triangulum galaxy, M33 possibly, plus any dwarfs, will fall in as well to form one big elliptical or diffuse galaxy. Our local group will become one large Milky Andromeda hybrid, sometimes playfully called Milkomeda. The notion of cannibalism is stark, but there's a constructive side. Each merger brings new material. The mixture of gas can spur star formation. New stars, clusters, maybe even new nebulae and structures are born from the union. It is a mode of cosmic renewal. The halo's very existence as a blended repository of many origins gives the Milky Way a kind of genealogical richness. If you take one halo star, measure its chemistry, you might find, oh, it has very low magnesium relative to iron that matches stars from this specific dwarf galaxy's pattern. That star might truly be from a galaxy consumed 10 billion years ago. It's like an immigrant star now living in the Milky Way, but carrying the accent of its birthplace in its elemental makeup. In that sense, the Milky Way is a melting pot of stars from different lineages. Much like modern cities contain people from diverse origins, the Milky Way's halo contains stars from a variety of prior smaller galaxies. We can stand under the night and not know that a star twinkling above might have originated outside our galaxy entirely. But the science tells us that's likely the case for many halo stars. Let us imagine following a stream. We drift along a line of stars in the halo. They stretch before us, hundreds of light years wide, but tens of thousands of light years long, gently curved around the galaxy. They are relatively sparse compared to the disk. If you were in the middle of a stream, you might still have to travel many light years to go from one star to the next. But relative to the emptiness around, it's a marked overdensity, like a barely visible road in a desert. We follow it inward. It leads us to a dwindling remnant of a once proud dwarf galaxy, perhaps a tightly bound cluster of stars that was its core. We follow it outward. It fades into the background of the halo. Over time, even the stream will diffuse further, as stars in it gradually spread out due to slight differences in their orbits. Streams are transient over billions of years, eventually becoming part of the general smooth halo background. The concept of galactic cannibalism invites philosophical reflection. Nature seems harsh on these scales. Big galaxies eat little ones. But it's also just the flow of gravity, not driven by intention. And from the ashes of that process arises something new. A larger galaxy, possibly capable of forming new stars and even new planetary systems that would not have existed otherwise. So there's destruction, but also creation in a new form. Now, beyond streams, we should note that not all satellites are completely destroyed yet. Some still exist around us. The satellites are basically meal preparation in a sense. We've touched on that, but it's worth giving them their spotlight next, before they too eventually face either merging or just orbiting ad infinitum. So let's now visit those satellite galaxies. The companions currently in the Milky Way's retinue, orbiting like the moons of a planet, though on a much bigger scale, some destined to become the next star streams in the far future. Satellite galaxies. The Milky Way is not alone in the cosmic ocean. It is accompanied by a swarm of smaller satellite galaxies bound in its gravitational embrace. These satellites are galaxies in their own right, but much smaller and fainter than the Milky Way, and they orbit around our galaxy like tiny fish around a great whale. They provide a sense of context. Our Milky Way, large as it is part of a local community of galaxies. The two most famous satellites are visible to the naked eye from the southern hemisphere: the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC. These appear as hazy, cloud-like patches in the deep southern sky, so much so that early explorers thought them to be clouds, hence the name. In reality, they are dwarf galaxies. The LMC is a barred spiral or irregular galaxy about 163,000 light-years away, roughly 1/10 the mass of the Milky Way, containing on the order of 30 billion stars. The SMC is about 200,000 light-years distant, with perhaps a few billion stars. These two are likely a bound pair and have been orbiting the Milky Way together. They have had a huge impact on our galaxy. Their gravity may be tugging on our disk, possibly causing asymmetries and warps, and gas outflows from them, the Magellanic Stream we mentioned, are feeding our halo with fresh material. The Magellanic Clouds are rich in gas and still forming stars. They have vibrant nebulae like the Tarantula Nebula in the LMC, which is one of the most active star-forming regions in the local group, a cauldron of massive stars and supernova remnants. If we look at them with telescopes, we see a flurry of star clusters and nebulae. They are like miniature versions of galaxies that remind us of how the Milky Way might have looked when it was smaller, or how galaxies across the cosmos often appear. Beyond the clouds, the Milky Way has dozens of dwarf spheroidal galaxies as satellites. These are faint, fuzzy objects scattered around the halo, many discovered only in recent decades with deep imaging surveys. They have poetic names often after the constellations they're found in: Draco, Ursa Minor, Sculptor, Fornax, Carina, Sextans, Sagittarius, which we already discussed being cannibalized, and many ultra-faint dwarfs like Willman 1, Segway 1, Bootes 1, etc. These dwarfs typically have only a few million to a few tens of millions of stars. Some of the ultra-faints just thousands of stars. They are heavily dominated by dark matter, interestingly, meaning the visible stars are just a tiny fraction of their mass. They're like little dark matter mini halos with a sprinkle of stars. Because of this, they are dynamically very stable, lots of dark matter to hold them. They have very old stellar populations, indicating they stopped forming stars long ago. Perhaps their gas was stripped early by the Milky Way, or they used it up quickly. They appear as little smudges in telescopes, often requiring long exposures to discern from foreground stars. One might ask, how many satellites does the Milky Way have? The number keeps growing as we find fainter ones. Currently, known ones are on the order of 50 to 60. The bright ones can be counted on fingers: Magellanic Clouds, Sagittarius, and maybe a dozen classic dwarfs discovered mid-20th century. But newer digital sky surveys are revealing extremely faint ones that push the limits of detection. We suspect there might be even more, lurking in parts of the sky not fully surveyed or hidden by the Milky Way's disk, or simply too faint to pick out easily. These satellites orbit at various distances. Some, like the Magellanic Clouds, are relatively close, under 200 Li. Others, like Leo 1, are quite far, over 800 Li. They orbit in what seems like somewhat random orientations, though there's some research suggesting maybe some align in a kind of plane, or come in groups possibly associated with cosmic filament structures. It's still debated if there's a satellite plane, or if that's a chance arrangement. The gravitational dance between the Milky Way and its satellites can have effects. The LMC, being the largest, is thought to be on its first approach possibly. Some studies propose the LMC might have only recently been captured. If so, the halo of the Milky Way might be moving a bit in response. The center of mass of the Milky Way LMC system might shift, causing our galaxy to slightly wobble. Some recent papers discuss the idea that ignoring the LMC's influence could bias measurements of the Milky Way's mass. Each satellite galaxy is like a chapter in the Milky Way's story. Some might be future meals. Some might just remain satellites indefinitely. For example, ultra-faint dwarfs might not easily merge because they're so small and diffuse. They might just get gradually stripped away over time. Others, like Sagittarius, are clearly on the menu. The Magellanic Clouds might merge soon, in cosmic terms, say within 2 billion years possibly for LMC. Satellites are also interesting as laboratories. Being simpler and smaller, they help us test models of dark matter on small scales and star formation in tiny potentials. They show that not all galaxies look like grand spirals. The majority in the universe are actually these small dwarfs. Poetically, I think of the satellites as a retinue of companions or children of the Milky Way. If the Milky Way is a great tree, these are the saplings around its base, some of which will eventually be reabsorbed into the soil to feed the great tree. Others may be transplanted by cosmic currents. They remind us of scale. What's small and faint compared to the Milky Way might itself hold thousands or millions of stars, and likely countless planets. Yes, consider that too. Each dwarf galaxy, even if it has 1 million stars, likely has planets. Could there be life in a satellite galaxy, gazing at the Milky Way as a giant spiral in their sky? Perhaps a planet in the LMC has a view of our galaxy somewhat like we see Andromeda, a big object in their night sky. Quite a perspective. Culturally, the Magellanic Clouds were known to peoples of the southern hemisphere for millennia. European explorers in the Age of Sail took note of them during voyages, hence named after Magellan by Pigafetta, though many indigenous cultures had their own names. They have always been a curiosity. What are these patches? Only in the 20th century did we measure their distance. Harlow Shapley did important early work on the SMC's distance using variable stars, and realized they are separate galaxies outside our own. The awareness that the Milky Way had companions was part of the bigger picture. Not only is the Milky Way not the whole universe, as the great debate settled by recognizing other galaxies, but even our galaxy itself has a system of smaller galaxies around it, a sort of microcosm of the macrocosm. We have our own mini-local group around just us. One of the nearest dwarf satellites is the Canis Major overdensity, discovered around 2003, which might be the core of a dwarf galaxy in process of merging, only 25,000 Poundsley from the center, which is inside the disk's radius. It's controversial, but there is evidence of a cluster of stars near Canis Major direction that could be a merging dwarf. If true, it's basically getting eaten now, and might be responsible for some rings of stars in the disk, like the Monoceros ring. This shows how the line between satellite galaxy and galactic structure blurs when cannibalism is happening. In the cosmic future, after Andromeda merges and everything settles, likely many of these current satellites will either be part of the big elliptical or flung out. Right now, they are like little birds around a big one, but when big birds come together, Milky Way plus Andromeda, the flock gets reconfigured. To visualize satellites, think of a three-dimensional model. At the center, the Milky Way disk. Dotted around at various distances, small fuzzy blobs. Some closer in, Sagittarius trailing streamers. Some mid-range, LMC, SMC, Fornax, etc. Some far out on the fringe, Leo Were, near edge of our halo. They each orbit at tens to a couple hundred kilometers speeds in some orbit. Over billions of years, we'd see them swarming, occasionally spiraling in. Interestingly, satellites can also survive if in stable orbits, especially if they're in a distant orbit and not a lot of dynamical friction, which slows down orbits of big objects moving through halos. Ultrafaints might hang around indefinitely if not disturbed. The LMC, being relatively massive, will probably spiral in faster due to dynamical friction. It's like how in a fluid, a big object slows quicker than a small one due to drag. We should also mention satellites like Ursa Minor Dwarf, Draco dwarf, faint but historically known, discovered in 1950s from photographic plates. And Fornax dwarf has some globular clusters of its own, a dwarf galaxy that has its own satellites, mini globular clusters, adding layers. So, the Milky Way is a system with subsystems. It's hierarchical. As part of our journey, perhaps now we stand metaphorically at the edge of the Milky Way's domain, looking at a sky not dominated by a single galaxy, but by many small companions scattered around. Perhaps from a vantage point in the halo, we could see the Magellanic Clouds off to one side, maybe glimpses of other dwarfs as faint smudges if our eyes could integrate light long enough. It would emphasize that the Milky Way is the central hub of a small cluster of galaxies. With satellites in mind, one naturally wonders, at the core of each satellite, is there something like a black hole or remnant? Possibly the LMC likely has one, others might not. Dwarfs might have only intermediate mass or none. But we know the Milky Way has one for sure at the center. And not just the central black hole. There are stellar mass black holes and other remnants peppered throughout. Let's now contemplate those black holes and remnants that permeate the galaxy after millions of star lives. The skeletons in the galactic closet, so to speak. Black holes and remnants. Throughout the Milky Way, hidden in the darkness, lie the corpses of stars, white dwarfs, neutron stars, and black holes, the remnants left when stars die. These objects are the end states of stellar evolution, and they are as much a part of the galaxy as the shining stars, though they emit little or no light of their own, apart from some exotic behaviors. In a sense, they are the galactic ancestors, the silent remnants of previous generations of stars that have completed their life cycle. Start with white dwarfs. These are the exposed cores of low to medium mass stars, like the Sun, after they shed their outer layers as planetary nebulae. A white dwarf is about the size of Earth, but with mass around that of the Sun, incredibly dense. Our galaxy is teeming with them. Every star less than about 8 times the mass of the Sun will end as a white dwarf. Given the Milky Way's age, billions of such stars have already gone through that process. It's estimated there are many billions of white dwarfs in the Milky Way. They quietly cool and fade over time, a process that takes longer than the current age of the universe to go completely dark. So even the oldest white dwarfs, perhaps 12 billion years old, still glow faintly red or infrared. In the thick disk and halo, one can find very old, cool white dwarfs that are barely luminous. These are sometimes called black dwarfs in the making, though not fully black yet. The Hubble Space Telescope has observed some of these ancient white dwarfs in globular clusters, giving us clues to ages. They're neutron stars. These are the collapsed cores of massive stars, 8 to 20 solar masses originally, that went supernova. They cram more mass than the Sun into a sphere only about 20 kilometers across. A neutron star is so dense that a teaspoon of its material would weigh billions of tons. There are likely hundreds of millions of neutron stars in the galaxy, though we only detect those that reveal themselves via radio pulses or X-ray emission, etc., a small fraction. Many neutron stars are observed as pulsars, lighthouses of radio or even optical X-ray beams sweeping the sky. The Milky Way pulses with thousands of known pulsars, each a neutron star spinning rapidly. Some spin hundreds of times per second, millisecond pulsars, often found in globular clusters or as remnants of certain binary evolution channels. These are like cosmic clocks, and they even help us detect gravitational waves' background or probe the interstellar medium via dispersion of their signals. Neutron stars also can be in binary systems. Sometimes 2 neutron stars orbit each other. We've detected those by their gravitational wave in spiral, like the famous one that produced both gravitational waves and a gamma-ray burst observed in 2017. Some neutron stars pull gas from a companion, flaring as X-ray binaries or even undergoing occasional outbursts when that gas triggers nuclear fusion on the neutron star's surface. These are X-ray bursters. And then, black holes. Aside from the supermassive one at the center, The Milky Way is littered with stellar mass black holes, formed by the collapse of stars above roughly 20 solar masses, or from mergers of neutron stars, etc. How many black holes? Possibly tens of millions. Each typically 5 to 15 times the Sun's mass, some more if formed by mergers. They are invisible unless actively accreting, pulling in gas, which then emits X-rays. Many have been found as X-ray binaries, where a black hole orbits a normal star and strips gas from it, forming a hot accretion disk that emits X-rays. Famous examples: Cygnus X1, the first strong black hole candidate, which is a stellar black hole consuming mass from a blue supergiant, or V404 Cygni, another volatile black hole binary that has dramatic outbursts. Most stellar black holes, however, might just roam quietly. One was recently found via gravitational microlensing. It passed in front of a background star, and the star's light brightened as the black hole's gravity bent it. That was our sign of an isolated black hole. The detection suggested a 7 solar mass black hole about 5,000 light away, dark and solitary. These remnants, white dwarfs, neutron stars, black holes, essentially form a kind of invisible substructure in the Milky Way. If you could see them all with some special glasses, the galaxy would have a faint glow or speckles from myriad white dwarfs in the disk and bulge, little spark-like pulsar beacons, point-like masses warping light, black holes. There's even speculation about intermediate mass black holes, hundreds to thousands of solar masses, possibly lurking in the centers of some globular clusters or dwarf satellite cores. We should also consider black hole binaries merging. LIGO detects such events likely from distant galaxies, but they could happen in our galaxy too, though none detected from within our galaxy yet, because they are rare per galaxy. If two black holes merge in Milky Way, it would release a burst of gravitational waves that we could detect. And neutron star mergers, aside from gravitational waves, they can eject heavy elements. So some of the gold or platinum on Earth might owe to a neutron star collision in the Milky Way's past that seeded heavy elements into a gas cloud that formed our solar system. The presence of remnants also provides continuity. A star dies, but part of it lives on as a remnant. For example, when the star that went supernova to create the Crab Nebula did so in 1054 AD, seen by Chinese astronomers as a guest star, it left behind the Crab pulsar, which still spins and powers the nebula's glow. The Milky Way likely experiences a supernova roughly once every century or so, though it's been a while since one seen by the naked eye, possibly because dust obscured a few. Each supernova adds a neutron star or black hole to the population. Also consider planetary nebulae, the colorful shells of gas from red giants casting off their layers. At the center of each is a new white dwarf. The galaxy has thousands of planetary nebulae visible, each an announcement: a white dwarf is born here. They are ephemeral. The nebula fades after 10,000 years, leaving just the white dwarf. The distribution of remnants is interesting. White dwarfs are everywhere: thin disk, thick disk, bulge, reflecting where stars like the Sun and smaller have lived and died. Neutron stars and black holes are mostly from massive stars, which mostly form in the disk, spiral arms. So their remnants should be in the disk, though some get kicked at birth. Pulsars often have high velocities due to supernova kicks, launching them out of the plane. Some even escape the galaxy if the kick is strong. So neutron stars might have a thicker distribution due to kicks. Black holes might get smaller kicks, maybe some kicks if asymmetry in supernova. So there could be black holes sailing in the halo or escaping as well. One evocative element: some remnants become zombie stars. White dwarfs can accrete material from companions, and if they reach 1.4 solar masses, Chandrasekhar limit, they explode as type Ia supernovae, which are important standard candles for cosmology. So even after death as a white dwarf, a star might have a spectacular thermonuclear rebirth explosion. Neutron stars too can have second lives, spinning back up by accreting matter, Millisecond pulsars are old neutron stars sped up by binary accretion, turning them into whirling beacons again. And black holes might occasionally flare if they consume a passing gas cloud, or even tear apart an unlucky star that wanders too close. Though that's more for big BHs like the center BH. Stellar black holes have small reach, but can still disrupt planets or smaller stars maybe. So, the Milky Way is somewhat of a graveyard entwined with a nursery. New stars are born from gas, often enriched by the deaths of old stars. And the dead stars themselves persist as these remnants, continuing to contribute gravitationally and sometimes in energy outbursts. Even smaller remnants, brown dwarfs, failed stars, substellar objects, and black dwarfs, cooled white dwarfs, none yet fully black, could be considered part of the population of faint objects bridging the gap between stars and remnants. Brown dwarfs are like forever fetal stars that never ignited hydrogen. There are likely as many, if not more, brown dwarfs than stars, lurking with low heat and faint infrared glow. They're not remnants, since they never fully were stars, but they add to the inventory of dark objects. The interplay of remnants could also create exotic phenomena. For example, a neutron star and a white dwarf binary, or a black hole swallowing a neutron star, could produce interesting events like gamma-ray bursts, though those typically happen in distant galaxies. Philosophically, the existence of these remnants is a reminder of mortality and memory. The Milky Way carries its dead with it. Unlike living creatures where corpses decay and disappear, in the galaxy the corpses remain for eons, influencing the environment. The remnants contain clues of their progenitors, like pulsars have spin rates and magnetic fields telling of the original star's core. White dwarfs have composition layers that tell of how the star ended nucleosynthesis. One might imagine each remnant as a kind of memory stone. If we could read them perfectly, we'd know about the star that once shone. Some white dwarfs have atmospheres of hydrogen or helium or carbon, telling what outer layer was left. Some neutron stars have extreme magnetic fields, magnetars, hinting at properties of the collapsed core. As we sail around the galaxy, every now and then we might pass invisible mass points, a black hole here, a neutron star there. Only a chance X-ray or radio emission or gravitational lens effect gives them away. Also, not to forget supernova remnants, not the compact object, but the blast wave and expanding cloud of gas like the Veil Nebula or Cassiopeia A's shell. These are ephemeral compared to the remnant core, but they, for a few thousand years, mark the spot of a stellar death like a wreath. The galaxy has many supernova remnants, observable in radio or X-ray, many more unobserved likely. They contribute to heating cosmic rays, etc. Thus, black holes and remnants add a quiet, somber layer to the Milky Way's composition. Unseen but present, silent but significant. They also connect to next topic, the central black hole we covered, and the future collision with Andromeda will eventually see black holes merge too, the central ones. But first, let's focus on that future collision. However, perhaps it's good narrative to mention, as time goes on, these remnants accumulate. Far in the future, after star formation ceases, trillions of years ahead, the galaxy will be mostly remnants. White dwarfs turn to black dwarfs, neutron stars cooled, maybe proton decay gone, black holes slowly evaporating via Hawking radiation over unimaginable times. That's the ultimate fate scenario. So in a way, these remnants are hints of what the galaxy will become in the distant, distant future. A graveyard with no new stars, just ghosts slowly fading. But before that final fade out, a dramatic event awaits. The collision with Andromeda, M31. That's a nearer term, in billions of years, future, that we should explore now. The future collision with Andromeda. In the cosmic dance of galaxies, the Milky Way and the Andromeda galaxy, our nearest large neighbor, are destined to collide. It's a fate set by gravity, a meeting foretold by the motions we observe today. Approximately 4 billion years from now, when our sun will be approaching old age, the serene night sky as we know it will undergo a radical transformation as Andromeda draws near, eventually merging with the Milky Way in a grand embrace. Let's set the scene. Andromeda, also called M31, is currently about 2.5 million light-years away, visible as a faint smudge in the constellation Andromeda. It's a spiral galaxy, somewhat larger than the Milky Way, perhaps containing 1 trillion stars. We are on a slow collision course. Andromeda is moving towards us at about 110 kilometers, as seen by the blue shift of its light. There's also likely some sideways motion, but even with that, simulations suggest a collision is likely given the strong gravitational attraction within our local group. Fast forward a couple billion years. Andromeda looms larger in the sky. To future inhabitants of Earth, if any remain or if Earth is still habitable then, as the sun will be heating up, Andromeda might appear as a giant spiral, filling a good portion of the sky, growing brighter and more detailed each eon. Its spiral arms could become discernible, and its central bulge would shine like a hazy second Milky Way band across the heavens. As the two galaxies near, their gravitational interactions will begin to disrupt both. Long before the cores meet, their halos and outer disks will clash. Gas clouds in the outer regions might slam into each other, triggering bursts of star formation. So we may see bright new star clusters and nebulae igniting in the collisional interface. The sky might become littered with brilliant O-type star clusters as the galaxies disturb each other's gas. Eventually, the galaxies will interpenetrate. Unlike a car crash, stars mostly do not hit stars because of vast distances between them. Instead, the two stellar disks will pass through each other like ghosts, but gravity will yank on each component, distorting shapes. Tidal tails of stars might fling outwards, great arcing streamers thrown into intergalactic space. Perhaps some stars, and potentially their planetary systems, will be tossed into new, wildly different orbits, some even ejected into space. Our solar system might be largely unaffected physically. The chance of direct close encounters with another star is small even in a merger, though not zero. But the night sky would be chaotic, new constellations of unfamiliar stars, as Andromeda's stars mix with ours. The black holes at each galaxy's center, each millions or billions of solar masses, will spiral toward each other over time, eventually coalescing into an even more massive black hole, after performing a sort of gravitational dance that radiates gravitational waves. When those two black holes finally merge, they will send ripples through space-time. Some future gravitational wave observatory might detect the echo of that event if any observers remain. The merged black hole will likely become active, consuming gas shaken into the center, perhaps lighting up as a quasar for a short time, shooting jets of radiation. During the interaction, the structure of both galaxies changes. The orderly spiral patterns will become twisted and then dissolved. Over a few billion years of alternating passes, these collisions often involve the galaxies swinging through each other, then slowing, coming back for another pass, like oscillating before finally coalescing. The stars' orbits will randomize. Eventually, what emerges from the wreckage is not a spiral galaxy at all, but probably a giant elliptical galaxy, a more amorphous, three-dimensional ball of stars with no distinct disk or arms. This new galaxy has been nicknamed Milkomeda by some, a portmanteau of Milky Way and Andromeda. It will contain nearly all the stars of both galaxies, plus any satellites involved, but arranged in a new way, many on long eccentric orbits forming a huge elliptical distribution. The gas, much of it likely either used up in starbursts or heated and expelled, might not form a disk, so star formation might slow drastically after the merger consumes the easily formed stars. For any beings at that time, the concept of the Milky Way or Andromeda as separate entities will be meaningless. There will be just one great galaxy filling the sky with a golden glow of billions of stars in every direction. This collision is not something to fear on a human timescale. 4 billion years is far beyond human or even Earth's future. the Sun will be in a red giant phase in about 5 billion years, possibly swallowing Earth. But as part of the galactic story, it's a dramatic climax. Our galaxy, which has been relatively isolated aside from munching dwarfs, will meet its equal and merge, fundamentally altering its identity. Interestingly, the merging will likely bring in Andromeda's own retinue of satellites, and our own, mixing them all. Maybe the Triangulum galaxy, M33, another member of the local group, will get involved or orbit the merger. Many of the satellite galaxies might either merge into the big one or remain as orbiting clusters of stars or get flung out. From a vantage point within the merging galaxies, cosmic events like starbursts might be visible. Perhaps multiple supernovae popping off as new massive stars quickly evolve. Globular clusters could be jostled, and some might be thrown into intergalactic space or form anew from colliding gas clouds. The night sky during the merger would likely have many more bright stars due to starbursts and diffuse light from the mass of stars. Perhaps the concept of night might get a bit eroded at some phases as more light fills the sky. However, given the scales, even a merger wouldn't make the sky bright like day. It'd just have more interesting features. Galactic collisions also produce rings and shells sometimes in the stellar distribution, visible long after, and trails of stars might form tidal streams connecting outward. Once the dust settles, literally, much dust might be cleared by starbursts and AGN feedback. The new combined galaxy will shine for trillions of years as it slowly uses remaining gas, then coast into a long, dark era. But by then, local group has become one big, gravitationally bound island universe. And due to the accelerating expansion of the universe, distant galaxies would have receded beyond visibility. So in far future, the merged galaxy will be quite alone in terms of observable universe, apart from maybe its local cluster. But focusing back on now, the knowledge of this future event is one of the marvels of modern astronomy. We have essentially predicted a cosmic event far beyond any human timeframe. It gives a sense of inevitability, but also continuity, that the cosmos has its timetable and flows that will go on without us. If we put ourselves poetically into that future scenario, try to imagine Earth's sky, say 3.75 billion years from now. Andromeda's disk spans the sky, maybe tens of degrees across, a glittering spiral visible even in daylight, perhaps as a faint structure. Then, in 500 million more years, the first close pass occurs. The sky might erupt with new stars. Perhaps the Milky Way's band in the sky distorts into weird shapes as Andromeda's stars join it. In 1 billion more years, multiple bands or a chaotic scatter of stars overhead as everything mixes. By 6-7 billion years from now, a smooth, glowing ellipsoidal distribution of light in the sky with no Milky Way band at all, just an all-sky faint glow, maybe thicker toward the center of the new galaxy. All the while, as an observer, you would have had to withstand the sun's red giant expansion, etc. But perhaps humanity's far descendants could watch from some other corner, or through robotic eyes. It's a scene for science fiction, but one grounded in astrophysics. Galactic collisions are common in the universe. Many galaxies we see are in collision or merged. Our own just hasn't had a major collision recently. The last big one might be that Gaia Enceladus event 10 years ago. So the Milky Way has had time to be a nice spiral. Andromeda too had mergers. It has a big bulge indicating past action. Now these two big ones will make one larger elliptical. Ellipticals typically have older stars and less gas afterwards. One could wonder about life consequences. Any risk to the solar system? Direct collisions of stars are extremely unlikely. However, passing stars could disturb the Oort cloud, comets, and send comets inward, raising the risk of impacts for planets. Also, if the sun's orbit is altered, it could experience changes in environment, maybe moving to a region with more supernovae or radiation. It's possible that life on Earth by then is gone due to sun's evolution, but if not, the merger could bring some gravitational nudges. But Earth's existence is precarious with the sun's changes anyway. Our collision with Andromeda is often portrayed as violent, but in human terms, it's a slow-motion event spanning billions of years. It will not destroy either galaxy entirely, but transform them. It is an act of creation as much as destruction, creating a new galaxy from two. As we consider that future, it's a reminder that change is the constant. Even the majestic spiral of the Milky Way is transient on cosmic time. The cosmos builds and rebuilds structures over time. Nothing stays the same. Galaxies grow, merge, fade. Now, coming back to a present perspective, one might ask, how fast are we moving right now and toward what? Which leads to consider the speed of motion more generally, not just relative to Andromeda, but all the motions we partake in. We have touched on orbital speeds around the galaxy, but perhaps dedicate a section to the myriad motions, the speed of stars, of the sun, of the galaxy moving through the universe, etc., to capture the dynamic nature. In the darkness between the stars, a single light is failing. Once it shone brilliantly, a beacon of warmth in the cosmic night. But now it flickers with a fragile, unsteady glow. The star is dying. For millions of years it burned in a delicate balance, its fierce nuclear heart pushing outward against the relentless inward pull of gravity. It may have warmed planets, illuminated nebulae, and been a sun to some distant world, but nothing in this universe is truly eternal. Now its fuel is nearly gone, and that balance has tipped. Deep inside the star's core, the furnace that sustained it is running out of flame. There is a hush, where once there was the roar of fusion. Gravity, ever patient, tightens its grip, squeezing the core harder and hotter in a desperate last attempt to keep the lights on. The star trembles on the brink. Its outer layers, once held taut by the pressure of light from within, begin to slide inward under gravity's command. If we could hear across the vacuum of space, we might catch a deep, forlorn groan as the star's very structure gives way. In one final, agonizing moment, the core of the star collapses. Ages of stellar life are undone in less than a heartbeat. Matter, that was the star's heart, is suddenly rushing inward at a significant fraction of the speed of light. Atoms are smashed together, nuclei are crushed, and the temperature spikes to unimaginable levels. It's as though an enormous weight has slammed down on the star's core, squeezing it to a fraction of its former size. Then, like a compressed spring uncoiling, all that pent-up energy is released. In that instant, the star that had faded now explodes in a blaze of glory. A flood of energy bursts outward from the core. What was moments ago a dimming ember becomes a sudden supernova, a titanic explosion of light and matter. The star's outer layers, which were collapsing inward, are blasted back out into space. In the span of a single second, a celestial object the size of a sun is torn apart. The darkness of a quiet cosmic night is pierced by a bloom of brilliance. The dying star outshines its entire galaxy, a flare of radiance against the void, like a colossal flower unfolding in fire. Anyone watching from a nearby world would see their night sky ignite with a light greater than 1,000 suns. For a brief time, this supernova shines with ferocious intensity. Gases that once formed the star's flesh are hurled into space as glowing shreds. Petals of stellar material, incandescent hydrogen, helium, and new forged heavier elements expand outward in great filamentary veils. And then, as suddenly as it began, the brilliance starts to fade. The explosion exhausts its initial energy and begins to settle. Where once there was a star, there is now a vast, ghostly cloud expanding through space. In its center, a tiny, fiercely hot remnant may persist, perhaps the collapsed core, transformed into a dense neutron star, or perhaps nothing visible at all if even the core succumbed to an all-consuming collapse. The light of the supernova dims from blinding to merely luminous and continues to wane over weeks and months, until to most eyes, the sky returns to its familiar darkness. The star is gone. All that remains is an expanding shell of gas, a nebula glimmering faintly with the last light of the star's dying breath, and, if the star's heart survived, a small, strange object hidden at the center of that nebula. In the silent aftermath, the cosmos is quiet again. Yet in that silence lies not just an ending, but a new beginning written in the ashes. The materials ejected by the star are mixing with the interstellar medium, ready to become part of something new. Every star's death is written by the life that led up to it. To understand this final blaze of glory, to truly grasp why the star had to die and how its death will give rise to new light, we must step back and watch how a star lives. Only then can we appreciate the full story, how a star's life creates the conditions for its death, and how even in dying, a star brings new light to the universe. Eons before that final eruption, our star's story began in darkness, a different kind of darkness, filled with promise. In a cold, dense cloud of gas and dust adrift in the galaxy, something subtle but significant occurred. Perhaps the passing shockwave of an older star's supernova swept through the cloud, or two galaxies brushed past each other and stirred the cosmic dust. Whatever the trigger, a region of the nebula began to condense. Gravity, the same force that would eventually destroy our star, was the midwife at its birth. What began as a diffuse, invisible patch of hydrogen gas slowly gathered into a tighter clump. As the gas particles drew closer together, their mutual gravity grew stronger, pulling in more and more material. The cloud fragmented into pockets. One of these pockets would become our star. Within that shrinking globule of gas, matter rushed inward, and the density and temperature at the core of the clump soared. At first, it was just a protostar, a warm, thick knot of gas still shrouded by the cocoon of dust from which it formed. The newborn protostar did not yet shine with its own light in the visible spectrum, but it was heating up steadily. As it grew in mass, pulling in material from the surrounding nebula, it began to spin faster, much as a dancer spins faster when pulling in their arms. A swirling disk of leftover gas and dust flattened around it. Occasionally, the protostar's growth was so violent that it ejected some material back out along its poles in narrow jets, like cosmic geysers, carving through the surrounding gloom. If we could have seen inside the nebula, we might have observed multiple such protostars forming in a cluster, siblings born from the same cloud, each gathering their own disks. Our protostar, for a time, was just one glowing embryo among many in a stellar nursery. Gravity kept squeezing that protostar's core, tighter and hotter, until one day, after perhaps millions of years of slow compression, the temperature at the center crossed a critical threshold. The star's heart caught fire. Hydrogen atoms, which had been pressed together more and more fiercely, suddenly began to fuse with one another. 4 hydrogen nuclei merged into one helium nucleus, and in that transformation, a tiny fraction of mass converted into a tremendous amount of energy. This was the moment of birth. The protostar's hidden fire ignited into starlight. The cocoon of dust was blasted away by the newborn star's radiance, and it announced itself to the universe as a new sun. The star settled into a long adulthood, blazing contentedly in a steady golden glow, if it was of moderate mass like our sun, or maybe a brilliant blue-white, if it was much more massive, or a dim red, if it was smaller. Its core became a powerhouse of fusion, turning hydrogen into helium and flooding the interior with energy. That energy pushed outward as light and heat, creating pressure that held up the star's weight. Gravity pulled inward, thermonuclear fire pushed outward. The two forces balanced in a beautiful, stable harmony. Astronomers call this hydrostatic equilibrium, but one might simply think of it as the star's heartbeat, a steady outflow of energy keeping gravity's crush at bay. For the majority of a star's life, this balance persists. Our own sun, for example, has been in this stable phase, the main sequence, for about 4.5 billion years, and will continue similarly for about 5 billion more. During this time, the star changes very little to the casual observer. It shines with a nearly constant brightness, day after day, century after century, its surface seething and churning, but its overall output steady. If the star has planets around it, they bask in this steady glow. Life, as on Earth, might have the chance to arise and evolve under the star's reliable warmth. Yet even a star's life, though long compared to ours, is not truly eternal. The fuel in its core is finite. The larger and hotter the star, the faster it burns through its supply. A truly massive star, dozens of times heavier than the Sun, might exhaust its core hydrogen in only a few million years, an eye blink compared to the Sun's 10 billion year lifespan. A tiny red dwarf star, on the other hand, sipping its fuel frugally, can shine for hundreds of billions of years. But eventually, in every star, the day comes when the hydrogen in the core is mostly spent. The core, now largely helium ash, can no longer sustain the same rate of nuclear burning. The outward pressure begins to falter, and gravity starts to gain the upper hand. The star has reached the end of its youth and stands at the threshold of its first great crisis. The first sign of a star's impending death is a profound transformation. As the core's fusion ebbs, nothing is left to hold up the weight of the star's outer layers. Gravity pushes those layers inward, compressing and heating the core once again. Paradoxically, this new squeeze of gravity provides a temporary lifeline. Around the inert helium core, a shell of hydrogen, which was previously too cool to fuse, now becomes hot enough to ignite. The star gains a second wind. Hydrogen fusion resumes in a shell around the core, pumping out energy furiously. This causes the outer layers of the star to swell outward. The star's radius balloons to many times its former size. As the surface expands, it cools and reddens, much like a piece of metal glows red when cooler but white when very hot. The once steady yellow star becomes a red giant, bloated and luminous, but cooler on its surface, with a heart of helium ash hidden at its center. If this star once had orbiting planets, their fate is precarious. During its expansion, the star's atmosphere reaches outward dramatically. A world that was once comfortably distant may now be inside the star's tenuous outer layers. Mercury and Venus, for instance, will be engulfed when our sun becomes a red giant. Earth may or may not be swallowed whole. Some calculations suggest Earth might spiral outward due to the sun's mass loss, just evading direct consumption. But even if it isn't engulfed, it will be scorched beyond recognition. In either case, the inner worlds will be burned and likely destroyed. Imagine for a moment being on a hypothetical moon of a distant gas giant. Watching this happen, over thousands of years, your sun grows ominously larger and redder in the sky. By the end, it spans a huge portion of the heavens, a dim red Goliath casting an eerie copper glow. The heat is relentless. Oceans boil away, atmospheres escape, surfaces melt. The gentle star that nurtured life has transformed into a ruthless juggernaut. Inside the red giant, while the outer layers swell and cool, the core is contracting and heating. When the temperature and pressure in the helium core become high enough, a new kind of fusion begins. Helium nuclei start fusing into carbon and oxygen. For a star like the Sun, this onset of helium fusion can be sudden, a phenomenon called the helium flash, where the core ignites in a runaway burst of energy, though the energy is absorbed and does not blow the star apart. In more massive red giants, helium ignition is a more sedate onset. Either way, the star now has a new fuel. For a while, helium fusion in the core provides an internal energy source, which somewhat stabilizes the star again. The star's radius might shrink slightly, and its surface temperature might increase for a time, especially in stars a bit more massive than the Sun, which forms something called a horizontal branch state. For a period of time, the star finds a bit of equilibrium once more, quietly burning helium to carbon and oxygen in its center. But this reprieve is relatively short-lived on cosmic timescales. A star like the Sun will burn helium in its core for only a few tens of millions of years, a mere flicker compared to the billions of years it spent burning hydrogen. Eventually, the helium too is exhausted, and this time, the star's core is left with carbon and oxygen, elements that for a modest-sized star are effectively inert. The core is not hot enough to fuse them into heavier elements. Fusion grinds to a halt in the center once more. The inert carbon-oxygen core, incredibly dense and hot, continues to contract under gravity. But now something quantum mechanical and strange comes into play. The core's atoms are packed so tightly that the electrons, in effect, refuse to be squeezed any further. They generate a quantum pressure, electron degeneracy pressure, that halts the collapse. The core, perhaps the size of Earth, but with half the Sun's mass, is as compressed as it can get without triggering further fusion or collapse. Meanwhile, the star's outer layers have become unstable. Without a vigorous energy output from the core, nothing can hold on to those distant layers. In the star's final breaths, it begins to pulsate. With each pulsation, it coughs away great shells of its own gas into space. Gentle stellar winds grow into intense gusts, pushing the star's envelope outward. The red giant sheds its skin, layer by layer. Over some thousands of years, the star loses a significant fraction of its mass this way. What remains at the center is the hot, naked core, now exposed for the first time to the outside universe. The escaping outer layers form an expanding cloud around it. The core is fiercely hot, hundreds of thousands of degrees, and its ultraviolet radiation causes the receding gas to fluoresce. What was once the star's atmosphere now becomes a gorgeous planetary nebula, a glowing shell of multicolored gas stretching out into the void. These nebulae are among the most beautiful objects in astronomy. They take on fantastical shapes, sometimes a nearly spherical bubble, other times a bipolar structure like two facing cones, and often complex rings and halos. To early astronomers with small telescopes, some resembled the round shapes of planets, hence the name planetary nebula, though they have nothing to do with planets. Our dying star's cast-off layers might form a luminous ring or an intricate lace-like web. As the ultraviolet light from the central core floods outward, it excites different elements in the gas. Hydrogen glows red, oxygen glows green-blue, nitrogen can add touches of red as well. The nebula may appear as a haunting turquoise halo or a delicate rosy sphere embedded with filaments. Some planetary nebulae appear as if a cosmic iris had opened its eye in the depths of space, with the central star as the pupil. These structures are often symmetric and eerily beautiful, expanding at tens of kilometers per second into the surrounding darkness. Such a nebula doesn't last long, a mere few tens of millennia, before dispersing into the wider galaxy. As it expands, its gases cool and dilute, fading from view. One day, not far by cosmic standards, the nebula will merge back into the interstellar medium from which the star once formed. But while it shines, it creates an unforgettable tableau, the farewell gesture of a star like our Sun. At the center of the expanding nebula lies what's left of the star's core, a white dwarf. This object is the smoldering ember of the star, incredibly hot at first but destined only to cool over time. It is a sphere of carbon and oxygen about the size of Earth, but containing roughly half the mass of the Sun. A teaspoon of its material on Earth would weigh tons. Inside this dense core, matter is supported by electron degeneracy pressure. The electrons crowding each other provide the stiffness that prevents further collapse. The white dwarf is initially bluish-white from the immense heat of its exposed interior. With no nuclear fusion to replenish its energy, those fires have gone out forever. It simply radiates away its stored thermal energy into space. Over billions of years, it will fade from white to yellow to red, and eventually become utterly dark. At that final stage, it is sometimes called a black dwarf, a cold, inert cinder in which even the residual glow has died out. However, the universe is not yet old enough for any black dwarfs to exist. Our star's white dwarf will shine, albeit weakly, for longer than the current age of the universe before it truly goes black. There is a poetic notion that as a white dwarf cools, its carbon might crystallize like a gigantic diamond. In fact, observations hint that some old massive white dwarfs have partially crystallized interiors. One could imagine that in the far future, the core of our sun might become a diamond the size of Earth, drifting through the galactic night. For now, our white dwarf is still extremely hot and luminous in ultraviolet and X-rays, which is what lights up its planetary nebula. Over time it will fade, but during the nebula's brief glorious existence, the white dwarf is a brilliant pinpoint at the center, a cosmic tombstone marking where a star's heart remains. This is the fate that awaits our sun and other stars of similar mass. A gentle, if somewhat melancholy, end, a final flowering as a nebula, and the quiet retirement of the core as a white dwarf. No spectacular explosion destroys the star outright. Instead, it is a slow shedding of worldly goods, a final display of color and light, then a gradual fading into the night. It is a quieter death than the ferocious supernova we imagined earlier. Yet, from the perspective of the universe, even this mild death has great significance. The outer layers shed into space carry elements that the star forged in its later life, elements like carbon and nitrogen, produced during the red giant phase. These become part of the raw material for future stars and planets. The star's death, though calm, seeds the cosmos just as surely as a supernova does, if in a more modest way. In dying, the star gives back much of its substance to the galaxy. Still, one might ask, what if a star had been born much more massive? Not all stars go gentle into that good night. For those born with significantly more mass, 8, 10, or 20 times the mass of the Sun or more, the final act is far more violent. When a high-mass star exhausts its core hydrogen, it, too, balloons into a supergiant. A red supergiant if relatively cool, or possibly a yellow or blue supergiant depending on its mass and stage. Inside, it goes through a furious sequence of burning stages. Unlike a low-mass star, a massive star can fuse elements beyond helium because its core gets hot enough to ignite heavier and heavier fuel. After helium is used up, creating carbon and oxygen, the core contracts and heats until carbon can fuse, producing neon, magnesium, and other elements. When carbon is depleted, the core, now largely neon and oxygen, contracts and ignites those. Neon fuses to oxygen and magnesium. Oxygen later fuses to silicon and sulfur. Silicon eventually burns to produce iron. The star's interior becomes layered like a giant onion, concentric shells where different fuels are burning. Hydrogen in an outer shell, helium in a shell beneath that, carbon, oxygen, neon, and so on, with an iron core forming at the center. Each successive stage of fusion burns faster than the last. A process that took millions of years for hydrogen and hundreds of thousands for helium takes mere centuries for carbon, then only years for neon, months for oxygen, and perhaps days or even mere hours for the final burning of silicon into iron. The reason is that as the star steps up the ladder of elements, the efficiency of energy production drops, so it has to burn through the fuel much faster to sustain itself. Finally, the star's core is composed of iron and nickel nuclei. And here the chain of fusion terminates, because iron is a dead end in terms of energy. Fusing iron into heavier elements does not release energy. It actually consumes energy. The star has no more nuclear fuel that can produce an outward push. The iron core grows to a critical mass, about 1.4 times the mass of the Sun, though compacted into a sphere only perhaps the size of Earth. At that critical point, The core can no longer support the tremendous weight of the star's envelope pressing down on it. In less time than the blink of an eye, the core collapses. Gravity wins decisively, catastrophically. The core's atoms are crushed together so forcefully that electrons are shoved into protons, turning them into neutrons and neutrinos. The entire core, which moments before was the size of a small planet, implodes to a sphere perhaps only a couple of dozen kilometers across, like a city-sized ball of neutrons. This collapse happens with incredible speed, less than a second. The infalling material reaches densities similar to an atomic nucleus. It's as if an object the size of the Earth suddenly became the size of a city. The violence of it is difficult to imagine. The collapse is eventually halted by the hard core of neutrons. Think of it like a rubber ball hitting a wall. The core bounces a little, sending a shockwave outward. At the same time, in that brief moment of formation, the new neutron core releases an immense burst of neutrinos. These ghostly subatomic particles rarely interact with matter, but so many are produced, carrying off about 99% of the collapse energy, that they impart a shock to the overlying stellar material. The combination of the rebound and the neutrino blast causes the star's infalling layers to explode outward. The result is a titanic supernova explosion, the same kind of event we described at the beginning. The outer parts of the star, by now expanded into a supergiant, are blown off in a tremendous blast, racing into space at a significant fraction of the speed of light. The energy released is almost unimaginable. For a brief period, the exploding star can radiate more energy than all the billions of other stars in its galaxy combined. If such a supernova occurred within a few dozen light years of Earth, it could disastrously affect our biosphere. Fortunately, no star currently that close is poised to explode in this way. The nearest candidate, Betelgeuse, is about 600 light-years away. But even at thousands of light-years, a supernova can be visible to the naked eye. Historical records around the world tell of new stars appearing in the sky. These were supernovae in our own galaxy. In 1054, observers in East Asia, and possibly North America, according to some petroglyph interpretations, recorded a brilliant star in the daytime sky. Unknown to them, they were witnessing a supernova whose remnant is the Crab Nebula. In 1604, astronomers observed another bright supernova, later called Kepler's supernova. Those events were in our Milky Way. Supernovae in nearby galaxies have also been visible to the naked eye, such as one observed in 1987. If Betelgeuse were to explode, future generations would see a star as bright as the moon for weeks on end, a celestial beacon announcing the death of a supergiant. As the star explodes, profound things happen inside the blast. The high temperatures and rapid changes trigger nuclear reactions that create new elements. All the elements heavier than iron that the star couldn't produce during its life are now synthesized in the furnace of the explosion. Gold, for example, and iodine, uranium, and many others are forged in seconds by rapid neutron capture and other processes. These precious metals and heavy elements are incorporated into the ejected gas that races outward. The debris of the star enriches the surrounding space with a myriad of elements that did not exist in such abundance before. And what of the star's core? After the supernova, if the core's mass is below a certain threshold, around 1.5 to 2 times the sun's mass, it stabilizes as a neutron star, a city-sized, ultra-dense object made mostly of neutrons. If the core is above that threshold, for very massive stars, not even the neutron pressure can hold it up, and it continues to collapse into a black hole, a region of space-time with gravity so strong that not even light can escape. Thus, the ultimate fate of the core is decided by the star's mass, neutron star or black hole. In either case, neutron star or black hole, something astonishing remains where the heart of the star once was. Meanwhile, The rest of the star has been blasted into space, forming a supernova remnant that will expand and fade over thousands of years. A core collapse supernova is one of the most magnificent events in nature, the violent death of a massive star. It is an ending on a grand scale, sudden, forceful, and final. And yet, in that destruction lies a kind of creation. The supernova scatters heavy elements that will someday become part of new stars, new planets, perhaps new living beings. Without such supernovae, the universe would lack most of the complex atoms that make up planets and life. So, the star's death, though a dramatic annihilation, is far from pointless. It is, in a sense, sacrificial, a star giving back to the cosmos all the elements it forged in life, and even creating new ones in death, fertilizing the galactic fields for the generations to come. Now let us consider this elemental alchemy more broadly. How, over the history of the universe, stars have served as the forges of the elements. From the hearts of living stars to the violence of their deaths, the chemical elements that compose our world and our bodies have been built up. In addition to hydrogen and some helium, which came from the Big Bang, all other naturally occurring elements were synthesized by stars. Stars in their long, stable lifetimes fuse lighter elements into heavier ones. In their cores, hydrogen becomes helium. When hydrogen is exhausted, helium fuses into carbon and oxygen. Later, in massive stars, carbon may fuse into neon and magnesium, oxygen into silicon, and silicon into iron. These processes happen over millions of years inside stars and produce most of the elements up to iron on the periodic table. The next time you glance at a periodic table, know that each element there has a cosmic pedigree: carbon, oxygen, nitrogen. These were made in star cores. Elements like silicon and sulfur in supergiant stars. Iron produced in the last gasp of a massive star's life.
What about elements heavier than iron, such as gold, lead, platinum, or uranium? These require special, extremely energetic conditions to form. Many are created during supernova explosions, when the flood of neutrons and the intense energy allow atomic nuclei to capture neutrons rapidly and build up into heavy elements, a process called the R process. Still others, especially some of the heaviest like gold and platinum, are now thought to be primarily forged in the colossal explosions that occur when two neutron stars collide. We'll talk about those later. There are also slower processes in aging giant stars, the S process, that builds certain heavy elements over longer periods and gently disperse them via stellar winds. But in general, the universe's inventory of elements beyond iron has been greatly enhanced by violent deaths, supernovae, and neutron star mergers.
Consider some examples of this cosmic alchemy. The iron in your blood's hemoglobin was forged in the core collapse of a massive star long before the Earth formed. The oxygen you breathe was cooked in the core of an ancient star and later scattered into space by a stellar wind or explosion. The calcium in your bones was built up in a giant star and cast off in its old age. Carbon, the backbone of life's chemistry, was created by the triple alpha fusion of helium in the core of a red giant star. Even rare elements like iodine, essential to biology in trace amounts, or gold, treasured and malleable, have origins in stellar cataclysms. Iodine likely in supernovae, and gold in the mergers of neutron stars that send debris rich in precious metals into space. Every atom of every element heavier than hydrogen that we find on Earth and in our bodies has traveled through a star. We are, quite literally, made of stardust. The very first generation of stars in the universe, billions of years ago, soon after the Big Bang, had only hydrogen and helium to work with. They forged the first heavy elements and spread them around via supernovae. Subsequent generations of stars were born from gas clouds already seeded with those heavier elements, which meant those stars could produce even more complex elements when their turn came. Over cosmic time, each cycle of star birth and death has enriched the galaxies further. By the time our solar system formed about 4.6 billion years ago, the gas and dust from which the sun and planets condensed were laced with the output of countless prior star deaths. That is why Earth has a crust rich in silicon and iron, why we have water, oxygen plus hydrogen, why there is phosphorus and potassium and all the rest, because the materials had been pre-cooked in stellar furnaces. It's an astonishing connection. The existence of our planet and of us living beings is directly tied to stars that died before the sun was born. We think of those stars as long dead and gone, and they are. But their chemical gifts live on in everything we see around us. In a sense, those ancient stars are not truly gone because we remember them with every breath and every bite of food. Our very bodies are their memorial. We truly are made of star stuff. This isn't just a romantic notion, but a physical fact. The atoms that compose our bodies were assembled in stellar cores and distributed by stellar winds and explosions across the galaxy, later to clump and form new worlds and living creatures. The death of stars is intimately tied to the creation of the ingredients of life. Every death, in this cosmic sense, is a kind of rebirth elsewhere. A star once existed for billions of years and then perished, returning its substance to the universe in a moment. And from that substance, new life eventually emerged. It's humbling and ennobling all at once. We are the universe's way of recycling stellar material into consciousness. In dying, stars both destroy and create. They leave behind remnants, like white dwarfs or neutron stars, and scatter their enriched guts across space. Yet not everything of the star is lost in this process. Even as a supernova strews a star's outer layers across the galaxy, the core of the star often survives in a drastically altered form. From the wreckage emerges a stellar remnant that challenges our understanding, an object so dense and extreme that it's like nothing else in the universe. Now, we turn to one such remnant, the neutron star, to witness what becomes of a massive star's heart after the explosive fury of a supernova. Imagine a ball of matter roughly 20 kilometers, 12 miles, across, about the size of a city. Now imagine that this tiny sphere contains more mass than 1.5 suns. This is a neutron star. It's essentially the collapsed core of a massive star, compressed so much that atoms can no longer remain atoms. The crushing gravity forces electrons and protons to combine into neutrons, hence the name neutron star. The entire object is basically a single giant atomic nucleus, an enormous clump of neutrons packed together with incredible density. A neutron star's density defies common sense. A teaspoon of neutron star material would weigh billions of tons on Earth, roughly the mass of a mountain crammed into a spoon. The surface gravity of a neutron star is similarly mind-boggling, hundreds of billions of times stronger than Earth's. If you were to drop a pebble from a height of 1 meter above a neutron star's surface, it would hit the surface in a microsecond and release as much energy as a large bomb. Standing on such an object, if one could, is an impossibility. You would be flattened thinner than a sheet of paper by the gravity. Everything about neutron stars is extreme. The gravity not only crushes matter, it also warps space and time around the star. Light leaving the surface is redshifted, reduced in energy, by the struggle against gravity's pull. If you observed a neutron star up close, its intense gravity would act like a lens, bending the path of light. You could actually see parts of the far side of the star as bent light curving around it. Neutron stars also spin, often at astonishing speeds. The core of the star that became the neutron star was rotating, and as it collapsed, it conserved angular momentum, like a spinning ice skater pulling in their arms. What was a rotation of maybe 1 revolution per day can become 1 revolution per millisecond. Indeed,
Many neutron stars spin tens or hundreds of times per second. The fastest known spins around 716 times a second. These rapid rotators are called pulsars when they emit detectable beams of radiation. A neutron star typically has a strong magnetic field, inherited and amplified from the star's original magnetic field as it collapsed. If the magnetic axis is not aligned with the spin axis, the rotating magnetic field accelerates charged particles and produces beams of radio waves, and sometimes X-rays or gamma rays, that shoot out along the magnetic poles. As the star spins, these beams sweep around like cosmic lighthouses. An observer in the path of the beams will see the star pulsing on and off, hence the name pulsar. The first pulsars were discovered as very regular radio pulses, so precise that at first astronomers half-jokingly dubbed them LGM for little green men, thinking perhaps they were signals from an intelligent civilization. We now know they are one of the natural marvels of neutron stars. The magnetic fields of neutron stars can be unimaginably strong. The most magnetic ones, called magnetars, have fields about 1 trillion times stronger than Earth's magnetic field. Such a field can distort the electron clouds of atoms from thousands of kilometers away, and would erase a credit card on Earth from a distance halfway to the moon. If you somehow approached a magnetar, the magnetic forces would not only scramble your compass, they would disrupt the very molecular bonds in your body. Magnetars occasionally experience starquakes. Their intense magnetic fields put so much stress on the solid crust of the neutron star that it fractures. When a magnetar's crust cracks, the reconfiguration of the magnetic field can release a burst of high-energy radiation. In 2004, a magnetar on the other side of our galaxy erupted and bathed Earth in gamma rays. For a fraction of a second, that single neutron star flare outshone all the stars in the Milky Way. Neutron stars may be small, but they are powerhouses of strange and violent phenomena. Though a neutron star has no more fusion and is technically a dead star, it is far from inert. It begins its life immensely hot, trillions of degrees right after formation, cooling to millions of degrees fairly soon. It emits thermal radiation, mainly X-rays when young, and will take millions of years to cool to more normal temperatures. As mentioned, many emit beams as pulsars. They gradually slow down as they radiate energy. Over very long times, an isolated neutron star will cool and its pulses will weaken, making it harder to detect. These become so-called quiet neutron stars, basically cosmic cinders a few dozen kilometers wide. But even then, if such a collapsed star encountered another star or gas cloud, it could spring into action again by accreting matter and flaring up in X-rays. Neutron stars are like celestial tombs. They contain within them the remnants of a star's core, all its complexity crushed into a hyperdense state. They challenge our understanding of physics, matter on the verge of collapsing into a black hole. In fact, if you were to add just a bit more mass to a typical neutron star, piling on a few more tenths of a sun's worth, you could force it to collapse further into a black hole. They are right on the knife's edge, between existence and oblivion, and this makes them fascinating waypoints in the story of stellar death. They are not the absolute end, but a transformed state of matter, a stepping stone toward the most extreme phenomenon of all. Even more extreme than a neutron star is the fate of the most massive stellar cores, the birth of a black hole. If a stellar core has more than about 2.5 to 3 solar masses after a supernova, gravity overwhelms all possible forces that might hold the core up. The neutrons in a neutron star, which normally resist further compression, themselves succumb if the mass is too great. There is no known force in the universe that can support such a massive core against collapse, so collapse it does, all the way, effectively, to a point of infinite density, a singularity in theory. A black hole is an object, or rather a region of space-time, formed by this total collapse. Around the collapsing core, a boundary forms called the event horizon. This is not a physical surface, but a spherical region of space
around the singularity where gravity's pull is so strong that escape velocity exceeds the speed of light. Anything, including light, that comes within this horizon is trapped and inevitably drawn into the center. From the outside, the event horizon is the point of no return. It's as if the core has punched a hole in the fabric of the universe and disappeared. All that's left is an intensely gravitational presence. A black hole that comes from a star might contain a mass of, say, 5 or 10 suns, but the event horizon radius would be only on the order of a few tens of kilometers. For comparison, Earth's radius is about 6,400 kilometers. Imagine an object 10 times more massive than the Sun, crammed into a sphere the size of a small city. That is the scale of a stellar black hole. At the event horizon, not even light can escape, so by definition, the black hole is perfectly black. If you were viewing a black hole from a safe distance against a field of stars, you might notice a strange warping or bending of the background star field as their light detours around the black hole's gravity. But otherwise, you'd see only blackness in the region of the hole, hence the name. What happens if something, say, an unlucky spaceship or star, gets too close to a black hole? Tidal forces become extreme. Much like the moon causes ocean tides on Earth by pulling a bit differently on the near side versus the far side, a black hole's gravity can vary tremendously over short distances. For a small black hole, for instance, the gravity at a distance of, say, 1,000 kilometers from its center might be millions of times stronger than the gravity 1,100 kilometers out. That difference would stretch any infalling object into a long, thin shape. Scientists grimly term this process spaghettification. A person falling feet first toward the black hole would feel their legs being pulled much more strongly than their head, and the result would not be survivable, to put it mildly. For larger black holes, like those at galactic centers, the tidal forces at the horizon might be less drastic, and one might actually cross the event horizon seemingly unharmed. But as one continued inward, the increasing gravity gradient would ultimately spaghettify and crush any object long before reaching the central singularity. Black holes also distort time. To a distant observer, a clock carried by something falling into a black hole would tick slower and slower as it neared the event horizon, and it would appear to stop entirely at the horizon. In fact, the falling object itself would never be seen to actually pass through the horizon. It would just fade and redden and freeze at the edge from the distant observer's perspective. But from the point of view of the infalling object, or person, there is no abrupt sensation at the horizon. One could cross it without fanfare, aside from those tides, and only later realize there is truly no way out. Inside, all paths lead inevitably to the center, the singularity, in a very short amount of proper time. Because no information can escape from inside the event horizon, what lies at the singularity remains one of the great mysteries of physics. Our current theories break down under those conditions of infinite density. It's possible that, in the real universe, singularities might be smoothed out by some quantum effect we don't yet understand, or perhaps they might even connect to other regions of space-time as speculative wormholes. But as far as observations are concerned, a black hole's interior is beyond our reach. From the outside, however, black holes do have measurable properties: mass, spin, and electric charge, though astrophysical black holes are typically uncharged. Many stellar black holes spin rapidly because the star's core had rotation, and that angular momentum is preserved. A rotating black hole drags space-time around with it, an effect called frame dragging. It can also power jets of high-speed particles if it's actively accreting gas. The rotational energy and magnetic fields can push some infalling plasma out along the poles. In binary systems, a black hole can tear matter from a companion star. That matter swirls into an accretion disk around the black hole, heating to millions of degrees and emitting X-rays and even gamma rays. Such systems are often detectable as bright X-ray sources. In fact, the first black holes were discovered because of their X-ray emissions in binary systems, like Cygnus X1, which alerted astronomers to a likely black hole siphoning gas from an unlucky companion star. It's ironic. A black hole itself emits no light, yet if it has a companion star or gas falling in, it can be among the brightest objects in the sky due to the energetic fireworks of that accretion. If isolated, a black hole is far harder to detect. It essentially becomes a patch of darkness. It can betray its presence only by gravitational effects, like bending light from background stars or influencing the orbits of nearby objects. In recent years, scientists managed to image the surroundings of a black hole directly. A global network of radio telescopes acting in unison, the Event Horizon Telescope project, captured the telltale silhouette of a supermassive black hole in a distant galaxy, seen as a dark shadow against a swirl of glowing gas. For stellar mass black holes, we have not imaged any directly, but their existence is strongly inferred by many observations. Black holes, especially those left by stars, are often quiet passengers in the galaxy. Astronomers estimate there are millions of them drifting through the Milky Way, remnants of ancient massive stars, essentially invisible unless they happen to interact with something. Indeed, one such dark wanderer was recently detected when its gravity magnified the light of a more distant star in an effect called gravitational microlensing, an exceedingly rare and fleeting event that nonetheless gave us a glimpse of an otherwise invisible rogue black hole passing through the galactic neighborhood. In the end, a black hole is perhaps the strangest legacy a star can leave. The star's entire identity, its thermonuclear brilliance, its shining surface, its complex layers, are all erased, collapsed into an infinitesimal mystery. What remains is pure gravity, a warp in space-time, a trap from which nothing can return. And yet, even this is part of the life cycle of the cosmos. Black holes are not malevolent. They are simply another possible end state of stellar evolution. They even play a role in the ecosystem of the galaxy, stirring interstellar gas with their gravity and merging with each other to release new kinds of energy in the form of gravitational waves. Thus far, we have explored what happens to individual stars at the ends of their lives, planetary nebulae and white dwarfs for the smaller ones, supernovae with neutron stars, or black holes for the larger ones. But the story does not end with these remnants. These stellar ghosts, the white dwarfs, neutron stars, and black holes left behind, continue to drift through the galaxy, and though they are no longer active nuclear furnaces, they are far from irrelevant. In fact, our Milky Way is populated by billions of such remnants, and they quietly influence the evolution of the galaxy. For every star that currently shines in the night sky, there are many faded stellar corpses lurking invisibly in the dark. Imagine the Milky Way not just as a glittering river of light, but also as a vast graveyard of expired stars. White dwarfs, in particular, are extremely common. Practically every low to medium mass star that ever lived in the past 13 billion years of our galaxy's history is now a white dwarf, unless it had a companion and went supernova as a type Ia, which is less common. It's estimated there are many billions of white dwarfs in our galaxy, slowly cooling. Similarly, neutron stars populate the Milky Way in their hundreds of millions, a number gleaned from the vast number of supernovae that must have occurred over cosmic time. And black holes of stellar mass might number in the tens of millions, roaming quietly. These objects are hard to detect when they're isolated, but they are there. Their collective gravitational influence contributes to the mass of the galaxy, some of the missing mass that isn't in visible stars or gas. These stellar remnants are like ghosts, invisible to normal sight, since a white dwarf is very dim compared to a star, a neutron star often only detectable as a pulsar or X-ray source, and a black hole completely dark unless feeding. Yet, though ghostly, they still have physical effects. A white dwarf, for example, retains most of its star's mass. If it has planets or a companion star, it still exerts a gravitational pull on them. Neutron stars and black holes gravitationally tug on nearby stars if any pass too close, possibly altering orbits over millennia. In aggregate, the population of stellar remnants adds to the galaxy's mass distribution, subtly affecting the motions of stars and gas on large scales. Some stellar ghosts actively announce themselves under the right circumstances. A neutron star with a strong magnetic field spinning as a pulsar will beam radio waves into space. If Earth lies in the path of those beams, we detect a precise periodic signal, a cosmic lighthouse blinking across the void. The pulsar at the heart of the Crab Nebula, the remnant of the 1054 supernova, still powers that nebula with a wind of particles and electromagnetic fields, causing the nebula to glow in X-rays and optical light. Neutron stars can also wander through the galaxy at high speeds. Some are given a kick at birth by asymmetries in the supernova. A fast-moving neutron star plowing through interstellar gas can create bow shocks, like the shockwave in front of a speeding boat, compressing and heating the gas, leaving a trail that could one day seed new stars. Black holes, too, can make their presence known if they encounter matter. In a binary system, as mentioned, a black hole can steal gas from a companion star. That gas, swirling into the black hole, gets intensely hot and radiates X-rays. From Earth, we see such systems as bright X-ray sources. Sometimes the inflow isn't steady. Imagine the black hole biting off more than it can swallow, which can lead to spectacular X-ray flares or even jets of plasma being ejected at near light speed from the vicinity of the black hole's event horizon. We've observed such phenomena in so-called microquasars, stellar mass black holes, mimicking on a smaller scale the behavior of supermassive black holes in galactic centers. Even an isolated black hole might reveal itself by lensing the light of background stars, as mentioned, or by faintly glowing due to the accretion of diffuse gas in the interstellar medium. The combined effect of countless stellar remnants also contributes to the cosmic rays permeating our galaxy. Supernova remnants accelerate particles, protons, nuclei, electrons, to high energies. Many of those particles wander the galaxy as cosmic rays, eventually running into things like our atmosphere, where they create showers of secondary particles. Neutron stars, especially pulsars and magnetars, and black hole accretion disks, can also accelerate particles. These cosmic rays can alter the chemistry in interstellar clouds, catalyzing certain reactions, and may even affect planetary atmospheres over time. Even white dwarfs, the most silently fading of stellar ghosts, can have a later chapter under the right conditions. If a white dwarf is in a close orbit with another star, it can siphon gas off its companion. That gas can accumulate on the white dwarf's surface and episodically ignite in a burst of fusion, causing a nova, a sudden brightening of the white dwarf star system. The white dwarf remains intact, and the process can repeat, essentially a ghost star showing flashes of life by stealing from its neighbor. If the white dwarf accumulates enough mass from its companion to approach the Chandrasekhar limit, 1.4 solar masses, it could even detonate entirely as a Type Ia supernova, obliterating the white dwarf in the process. In that sense, even a dead star can, given the right circumstance, die a second death, taking part in one of the universe's grand explosions. Our galaxy's center houses the largest ghost of all, a supermassive black hole millions of times the mass of the Sun. While not a product of a single star's death, it's the result of many mergers and accretion events over the galaxy's history. It stands as an ultimate example of what gravitational collapse can lead to. This behemoth, lurking about 26,000 light-years from us, in the direction of Sagittarius, orchestrates the orbits of stars in the galactic core. Usually it's quiet, but occasionally it snags a passing star or cloud, producing energetic flares. It reminds us that even at the grandest scale, the remnants of cosmic evolution continue to shape their surroundings. Time is a key factor in how prominent these ghosts are. As millennia and millions of years pass, stellar remnants will increase in number. We live in an era when many stars are still in their shining prime, but far in the future, these remnants will far outnumber the bright stars. The galaxy will eventually become a darker place populated mostly by cooled white dwarfs, dim neutron stars, and black holes, plus diffuse gas. The living, burning stars will be few. In that distant epoch, the ghosts will truly dominate the scene. For now, though, they coexist with a vibrant stellar population. They are like an unseen foundation beneath the more obvious architecture of bright stars. They quietly contribute to the cycle of matter and energy. They provide stepping stones to further cosmic events, like neutron star mergers producing new phenomena. The story of stellar death doesn't end with the initial death. It continues as these ghosts interact, decay further, or sometimes combine in spectacular ways. We've touched on a few hints of even more dramatic events when these stellar remnants meet or interact. Indeed, some of the most breathtaking phenomena in the universe occur when death begets death, when two stellar corpses engage in a final dance or collision. Not all stellar deaths occur in isolation. Many stars are born in binary systems, and their fates are intertwined. Let's explore how binary relationships can lead to unique kinds of stellar demise, cataclysmic variables like novas, the exceedingly bright Type Ia supernovae, neutron star collisions that create gold and gravitational fireworks, and other cosmic pas de deux that enrich the drama of stellar death. Consider a binary star system where one star dies before the other. For instance, imagine a sun-like star and a slightly more massive companion orbiting each other. The more massive star evolves faster, becomes a red giant, and eventually sheds its outer layers, ending up as a white dwarf, while its companion is still in a relatively normal state, perhaps a main sequence star or a red giant of its own later on. Now you have a white dwarf and a second star in a binary. The white dwarf is a tiny, dense object with powerful gravity, and if the two are close enough, it can begin pulling gas away from its still-living companion. The unfortunate companion's star finds its outer layers being siphoned off, spiraling onto the white dwarf. This transfer of mass at first might be a gentle stream, invisibly making the white dwarf more massive. But as the stolen hydrogen from the companion accumulates on the white dwarf's surface, it grows denser and hotter until, flash, the layer of gas ignites in a runaway fusion reaction. In a matter of seconds or minutes, the accumulated hydrogen burns explosively into helium. The white dwarf's surface blasts off a shell of fusion ash into space. From afar, this system suddenly appears to brighten enormously. What was a faint star may become visible to the naked eye as a new star in the sky for a few weeks. This is a nova, Latin for new star. It's not the birth of a star, of course, but rather a flash from a dead star reigniting stolen fuel. In a nova, the white dwarf survives the explosion. It's akin to a stellar hiccup, however energetic. After the blast, the white dwarf can go back to quietly accreting matter from its companion, and after some years or decades or millennia, it might erupt again. Some systems are known as recurrent novae because they flare multiple times. The cycle can continue as long as there's a supply of fresh fuel from the companion, and as long as the white dwarf's gravity can pull material in a stable manner. These nova explosions, while dramatic, are relatively small on the cosmic scale. They don't destroy the star and are minuscule compared to supernova. However, under certain circumstances, a white dwarf in a binary can undergo a far more devastating event. If the white dwarf accretes enough mass from its companion, pushing its mass closer to that Chandrasekhar limit, 1.4 solar masses, the pressure and temperature in its core can become high enough to ignite carbon fusion in an uncontrolled way. Remember, this is a white dwarf made of carbon and oxygen. Unlike hydrogen or helium, when carbon in a degenerate white dwarf core ignites, the burning doesn't gently expand the star to regulate the temperature. because the white dwarf's pressure is supported by quantum degeneracy rather than thermal pressure. An increase in temperature doesn't lead to expansion and cooling. The result is a runaway thermonuclear reaction, consuming the entire white dwarf within seconds. The white dwarf detonates completely in one of the most brilliant pyrotechnics the cosmos offers, a Type Ia supernova. In a Type Ia supernova, a tiny Earth-sized object, the white dwarf, is obliterated, unleashing a titanic amount of energy and forging elements like iron, nickel, and cobalt in vast quantities. There is no compact remnant left. No neutron star or black hole remains, because the entire white dwarf is now an expanding cloud of glowing debris. Type Ia supernovae shine with such consistent peak luminosity, about 5 billion times the luminosity of the Sun, that astronomers use them as standard candles to measure distances across the universe. They are cosmologically important. Observations of distant Type Ia supernovae revealed the accelerating expansion of the universe, attributed to dark energy. But on a personal level, they are another way that stars die with a creative flourish. They spread iron and other intermediate weight elements far and wide, elements that may not be as abundant in core collapse supernovae of massive stars. So in binary systems with white dwarfs, we have a spectrum, from gentle novae to total annihilation in Type Ia supernovae, depending on how much mass the white dwarf steals and how quickly. Now consider binaries, where both stars are massive enough to form neutron stars or black holes. There are binary systems where one star explodes as a supernova and becomes a neutron star. But the two remain bound, or become bound again if the kick isn't too strong. Eventually, the second star also goes supernova, possibly leaving two neutron stars orbiting each other, or a neutron star and a black hole, or two black holes. These pairs of dense remnants are essentially ticking time bombs. They spiral toward each other over very long periods as they radiate gravitational waves, ripples in space-time that carry energy away from the orbit. When two neutron stars finally collide, the event is cataclysmic on a different level. Picture two city-sized, insanely dense objects whipping around each other hundreds of times per second as they draw closer. In their last moments, they approach nearly a significant fraction of light speed. When they merge, enormous gravitational and nuclear forces come into play. The merged object can promptly collapse into a black hole, or, if enough support exists briefly, form a hypermassive neutron star for a short time before that too collapses. In the process, a huge mass of neutron-rich material gets flung out into space from the violently merging stars. This debris, rich in heavy elements, heats up and produces an ephemeral but brilliant glow known as a kilonova, so called because it's roughly 1,000 times brighter than a typical nova, though still dimmer than a supernova. The kilonova initially shines blue-hot from freshly synthesized radioactive elements. Then, as those nuclei decay, the glow becomes redder over days and weeks. It was by observing the light from such a kilonova, accompanying a gravitational wave event in 2017, that scientists confirmed that neutron star mergers manufacture heavy elements like gold, platinum, and rare earth elements in significant quantities. The very gold in jewelry here on Earth likely came from such an event in our galaxy's past. The neutron star merger also emits a burst of high-energy gamma rays, a short gamma ray burst, especially if jets form during the collision. These gamma ray bursts are some of the most luminous events in the universe, though very brief, lasting less than 2 seconds for the short variety, longer for collapsar-related bursts. If instead two black holes collide, imagine two invisible dark spheres merging. They release a purely gravitational scream, a burst of gravitational waves, as the only directly observable output. This was what LIGO detected in 2015. The final moments of two black holes merging, converting a few solar masses worth of energy into vibrations of space-time that stretched and squeezed the detectors on Earth ever so faintly. Such events were predicted by Einstein's general relativity and are now observed. They too are endpoints of binary evolution, two stellar mass black holes in a death spiral. There are other exotic binary interactions. A neutron star and a black hole could merge, likely gobbling the neutron star and producing gravitational waves and maybe a faint gamma burst. A neutron star and a white dwarf could collide under rare circumstances, or a black hole could slowly consume a white dwarf or neutron star, tidally shredding it. These scenarios are less commonly observed, but are theoretically possible in dense environments like star clusters. One more comparatively common binary death process. Classical novae we already discussed involve a white dwarf, but there's also a kind of middle ground event called a red nova, or luminous red nova, which occurs when two normal stars merge. While not as energetic as a supernova, it's a stellar death of sorts. The two stars cease to exist as individuals and become one star. These events can produce a significant outburst, as seen in objects like V1909 Scorpii or others, where contact binary stars spiraled together. The result is a single larger star, often shrouded in dust, and the process may eject a significant amount of the star's mass. It's a death in the sense that two separate stellar lives ended and a new one began. In all these binary cases, what's striking is how the presence of a partner star alters the outcome. A star alone might quietly become a white dwarf and sit there forever, but with a companion, it might reignite and explode. Two neutron stars alone drift through space. Together, they can create one of the most important sources of heavy elements and brilliant fireworks. From the gentle recurring nova that might just create some exotic isotopes and pretty displays, to the awesome Type Ia supernova that serves as a cosmic yardstick and forge of iron, to the mind-bending mergers of neutron stars and black holes that literally shake the fabric of space-time, binary interactions significantly enrich the tapestry of stellar death. They show that even in death, stars are not solitary actors. They can affect one another, sometimes saving their grandest drama for when they are together. Up to now, we have been describing what happens to stars and their remnants more or less from a theoretical perspective. But how do we know all this? Much of the science of stellar evolution and death has been pieced together by observing countless stars at different stages and by physics calculations that have been tested in various conditions. Still, one might wonder, no human has watched a star go through its entire life cycle. It takes millions to billions of years. So how can we be confident in this story? The answer lies in the incredible detective work of astronomy, using both light and other cosmic messengers to understand these processes. Humans have actually observed the deaths of stars for millennia, even if they didn't know what they were seeing. Ancient peoples recorded sudden appearances of bright stars that weren't there before, what we now recognize as supernovae or novae. They regarded them with wonder, sometimes as omens or messages from the heavens. For instance, in July of 1054, observers in East Asia noted a guest star near the star Zeta Tauri. It stayed visible in daylight for weeks. Today, we see the remains of that event as the Crab Nebula in Taurus. Inside it, a pulsar spins, the neutron star left from that massive supernova. In 1604, sky watchers, including the astronomer Johannes Kepler, observed a new star in the constellation Ophiuchus, Kepler's supernova, the most recent known supernova in our Milky Way. These historical accounts, though made without understanding the true nature of the events, are invaluable records. They tell us, for example, that supernovae can occur in our galaxy a few times per millennium. It's likely more have happened obscured by dust or mist due to being in the southern hemisphere, unobserved by Europeans or Far East observers. In modern times, we have developed an arsenal of instruments that allow us to catch stellar death in action across the universe. Telescopes and detectors now cover the electromagnetic spectrum from radio waves to gamma rays. And even beyond electromagnetic signals, we have neutrino observatories and gravitational wave detectors. When a massive star explodes in a galaxy millions of light years away, our optical telescopes see a pinpoint of light that wasn't there before. Robotic telescope surveys scan the sky nightly and automatically flag such new points of light or unusually brightening points. Professional and amateur astronomers then train their telescopes on them to gather more data. By splitting the light with a spectrograph, we see telltale fingerprints of certain elements, perhaps silicon and sulfur lines expanding at high speed, indicating a type Ia supernova, or hydrogen lines indicating a type 2, core collapse, supernova. The light curve, the way brightness changes over time, provides clues. A type Ia supernova has a characteristic rise and gradual fall. A massive star supernova might plateau, or have multiple peaks if complicated by circumstellar material. In fact, by studying many such events, astronomers have subclassified supernovae, type 2P, 2L, IN, IB, ICE, etc., which correspond to different ways stars meet their end. Some shed their hydrogen envelopes first, some don't, etc. When a supernova occurs relatively nearby, say in a galaxy in our local group, we can sometimes directly see the debris after the explosion fades. The Hubble Space Telescope and ground-based telescopes have monitored supernova remnants and even the actual positions of supernova events decades later to see the shockwave expansion. For example, supernova 1987A, which occurred in a companion galaxy to our own, the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, in 1987, has been observed continuously for decades. We saw a brightening as the shock hit a pre-existing ring of gas, previously expelled by the star, and we've been waiting for the possible emergence of a neutron star or pulsar within the debris. Only recently have there been hints of it. SN 1987A was a bonanza for learning. It was the closest supernova in centuries and was extensively studied across all wavelengths. Neutrinos are a novel way we confirmed our theories. Those ghostly particles from SN 1987A were actually detected in underground detectors on Earth, Kamiokande in Japan and others, a few hours before the visible light of the explosion reached us. This happened because neutrinos, which scarcely interact with matter, streamed out of the collapsing core immediately, whereas photons were trapped until the shockwave reached the surface of the star. The burst of neutrinos, just 24 of them detected, matched the predictions for a core collapse neutrino signal, providing direct evidence of what was happening deep in the star at the moment of explosion. It was a dramatic confirmation of stellar death physics. We felt the star's core collapse through neutrinos, then saw the star blow apart in light. In the past few years, gravitational wave astronomy has opened another new window. In 2015, the LIGO Observatory listened as 2 black holes merged, which was our first direct detection of gravitational waves. Then, spectacularly, in August 2017, LIGO and its European cousin Virgo detected a signal that indicated 2 neutron stars spiraling together. Within seconds, a gamma-ray burst was detected by orbiting satellites. Hours later, telescopes spotted a new transient glow in a galaxy about 130 million light-years away, the kilonova from that merger. Here we had essentially the complete story. Gravitational waves told us 2 neutron stars collided, gamma rays told us jets formed, and the kilonova's light, with spectra showing gold and other freshly made heavy elements, told us about the material ejected. It was perhaps the most observed astrophysical event in history, with dozens of telescopes joining in. This single event confirmed several theoretical ideas at once, that merging neutron stars produce short gamma-ray bursts and heavy elements. It was like witnessing the birth of elements, gold, platinum, etc., in real time. And it showed the power of combining different cosmic messengers, gravitational waves to pinpoint a cosmic death dance, and electromagnetic waves to witness its aftermath. Even black holes, which emit no light of their own, have become observable through their interactions. Aside from LIGO's detections of merging black holes, which produce only gravitational waves, we have observed stars orbiting our galaxy's central black hole over decades. These stars move in tight, fast ellipses, with one star, called S2, coming as close as 17 light-hours to the black hole, 4 times the distance of Neptune from the Sun, and whipping around at a few percent of light speed. By tracking these orbits, astronomers have confirmed the presence and mass of the central supermassive black hole. This achievement, in fact, earned the 2020 Nobel Prize in Physics, and as mentioned, we have even imaged the shadow of a black hole's event horizon for the supermassive black hole in galaxy M87, and very recently our own galaxy's center as well, by using radio telescopes spread across the globe. The image appears as a ring of light emitted by hot gas just outside the horizon, surrounding a dark area, the silhouette of the horizon itself. It's a stunning confirmation that the dark star predicted by general relativity is real. When it comes to observing stellar ghosts, pulsars have been detected by their pulses. Over 2,000 are known to date. Some pulsars are in binary systems, which allows us to test general relativity, such as the famous Hulse-Taylor pulsar, a neutron star pair that spirals inward exactly as gravitational wave emission predicts. White dwarfs have been observed in huge numbers as well, often through surveys like the Sloan Digital Sky Survey. We can even see extremely faint white dwarfs in clusters like M4, giving a hint that some are crystallizing as they cool. These observations line up with the theory that white dwarfs cool and fade over billions of years. Novae are observed fairly frequently in our galaxy. About 10 per year are seen, and many more likely occur on the far side of the galaxy hidden by dust. Each nova gives us insight into the accretion processes on white dwarfs. Some have even been observed to recur, e.g. RS Ophiuchi, which erupts about every 15 to 20 years. Supernova remnants, like the Veil Nebula or Cassiopeia A, have been mapped in detail by telescopes. In Cass A, the remnant of a supernova around 1680 AD, though oddly no one clearly recorded it at the time, astronomers have found the neutron star left behind, and they've even seen light echoes in surrounding dust that give clues to the original explosion. In X-rays, Cass A's image from Chandra shows an incredible expanding shell, with different elements separated spatially. For example, iron is more interior, oxygen and magnesium more outside, consistent with our understanding of how supernova nucleosynthesis and ejection work. Our ability to simulate stellar deaths on computers has also advanced. We can now create models that, for example, follow a massive star's collapse and explosion, and see how asymmetries can give a neutron star a kick, or how mixing can produce certain light curves. These models are tuned by matching them to observations, say, the light curve of SN 1987A, or the spectra of various supernovae. While some details are still being researched, like the precise mechanism that makes every core collapse supernova explode rather than implode entirely, neutrinos are key, but it's a complex hydrodynamic dance. The broad strokes are strongly supported by data. Thus, through a combination of direct observation across all wavelengths, and now beyond light, historical evidence, laboratory physics, and computational modeling, we've assembled the story of stellar life and death. Each new technological leap, from Galileo's first telescope, to spectroscopy, to space telescopes above our atmosphere, to neutrino detectors, to gravitational wave observatories, has added a piece to the puzzle, or confirmed a chapter of the tale. We no longer merely speculate about star death, we witness it. We have seen the X-ray glow of neutron stars feeding, the gentle wink of novae, the sky-filling blast of supernovae, the faint whisper of colliding black holes. Even now, somewhere in the universe, a star is living out its final moments. Perhaps in a distant galaxy, a red supergiant's core has just collapsed, neutrinos streaming out, a shockwave on the way. Within the next few hours or days, light from that explosion will start its journey across space. In a few years, maybe it will arrive at Earth, and robotic telescopes will catch a new star in their images. Alerts will go out, astronomers will turn their instruments to study it, and humanity will collectively witness another star's death in as close to real time as nature allows. With every such observation, our understanding deepens. We are, in a sense, collecting the final words of stars, listening to their swan songs, and learning from them. One day, we will face a very personal case of stellar death, that of our own sun. But fortunately, that is far in the future. Our sun is currently a healthy middle-aged star, shining steadily and nurturing a rich biosphere on the third planet from its warmth. Yet, like all stars, it must eventually exhaust its fuel and transform. What will that look like? And what will become of the Earth? Our sun is about 4.6 billion years old. It's roughly halfway through its main sequence lifetime. For the next few billion years, it will continue to fuse hydrogen into helium in its core, gradually getting hotter and slightly more luminous as the helium ash accumulates. In fact, the sun's brightness has increased by about 10% since it formed. In another billion years or so, that slow increase will make Earth significantly warmer, potentially too warm for complex life long before the dramatic red giant phase arrives. By around 5 billion years from now, the sun will have run out of core hydrogen. At that time, it will begin the transition into a red giant. The sun's core will contract and heat, just as we described earlier, and hydrogen fusion will ignite in a shell around the core, causing the sun's outer layers to expand tremendously. It's estimated that at its largest, the sun's radius will extend to somewhere around Earth's orbit. Perhaps a little less, perhaps a little more. The exact calculations are complex and depend on how much mass the sun loses as a red giant. Mercury and Venus will almost certainly be engulfed and vaporized. Earth's fate is uncertain. Some models suggest Earth will be swallowed by the sun's expanded atmosphere, dragged inward by tidal interactions, and incinerated. Other models suggest Earth might just barely survive, orbiting within the sun's outermost tenuous layers or just outside them after orbital expansion due to the sun's mass loss. Either way, the Earth's surface will be sterile. Long before the sun actually touches Earth, the increasing heat will have boiled away the oceans and stripped the atmosphere. The crust will glow red hot. For a while, Earth might resemble a desiccated rock, like Mercury, under the gigantic red orb of the sun filling the sky. By the time the sun is at its largest, even the outer planets will experience vastly increased solar heat. Mars might briefly enjoy Earth-like temperatures, though bathed in red light, but not for long. If any humans, or our far future descendants, are still around by then, they would have had to leave Earth, and perhaps the solar system entirely. Maybe they would take refuge in the outer reaches, on moons of Jupiter or Saturn, which might become temperate for a short period. Or more likely, humanity would undertake voyages to other star systems long before that. It's poignant to imagine that far future observers, perhaps the distant descendants of humanity or some other species that by then knows this story, could watch from a safe distance as the sun goes through its death throes. They might see the sun's color turn from yellow-white to orange to deep red as it expands. They would know, as they watch, that this was once the star that sustained the cradle of human civilization. The emotions such observers might feel blend sorrow at the loss of the sun's former life-giving form and awe at the grandeur of the transformation. As the sun's core continues to contract, it will eventually ignite helium fusion in a flash, as described earlier. The sun will shrink slightly and settle into a stable helium-burning phase for a time, becoming perhaps a bit less distended. It might then expand again for an asymptotic giant branch phase after helium is exhausted, undergoing some thermal pulsations, each expelling more of its outer layers. Finally, the sun will shed its outer envelope. The dying sun will create a planetary nebula,
perhaps a glowing shell of ionized gas expanding outward, beautiful in its complexity. Some models suggest the Sun's planetary nebula might be relatively faint, because the Sun is not as massive as the stars that make the showiest nebulae. But it will still be a sight to behold, a ring or bubble of color, marking where our star says farewell. At the center of that nebula will lie the Sun's core, a fresh white dwarf. It will likely be composed of carbon and oxygen, about half the Sun's present mass, compressed into roughly Earth's volume. It will be extremely hot, well over 100,000 degrees Celsius at the surface initially. It will cool slowly over billions of years. Once the surrounding nebula drifts away into space, the white dwarf Sun will remain, a small, dense, gradually cooling sphere. It will shine mostly in the ultraviolet initially, with perhaps a bluish-white hue if one could see it up close, then fade through the colors to red and eventually to darkness over trillions of years. The solar system, as we know it, will not survive this process intact. The inner planets will be gone or altered beyond recognition. The gas giants might migrate outward as the Sun loses mass, since the gravitational hold will weaken. The icy bodies of the outer solar system, Kuiper belt objects, Oort cloud comets, will largely drift away or get perturbed by the changing gravity. The final configuration might be a white dwarf with a few distant cold planets, perhaps Jupiter, Saturn, Uranus, Neptune, if they aren't lost, now wandering farther out, perhaps some moons or dwarf planets, frozen solid. Over enormous timescales, even those remaining planets might detach or be perturbed by passing stars. It is a sobering scenario, the demise of our warm and life-sustaining Sun. Yet, it is also strangely uplifting to know that the Sun's materials will not be lost. The planetary nebula cast off by the dying Sun will carry atoms that once made up our world out into the galaxy. Perhaps some of those atoms will eventually find their way into new star-forming clouds. In that sense, a piece of Earth and a piece of us will journey on, joining the great cycle of cosmic recycling. In fact, there is a theory that a supernova may have helped trigger the formation of our solar system over 4.6 billion years ago, based on certain isotopes found in meteorites that are byproducts of supernova nucleosynthesis. If true, then a star's death begot the Sun's birth. And now we see that the Sun's death will return the favor by contributing its matter to future generations of stars. The cosmic cycle continues. Now let's journey unimaginably far into the future of the universe, beyond not just the death of individual stars, but to the era when perhaps all stars have died. What happens after the age of starlight? The universe is about 13.8 billion years old. We live in what astronomers call the stelliferous era, age of stars, when galaxies gleam with billions of active stars. But stars consume fuel. Galaxies have a limited gas supply, and over time, star formation will slow. Astronomers project that star formation will continue on a declining curve for many trillions of years, gradually winding down as gas gets locked into long-lived dwarf stars or compact remnants. The smallest, most long-lived stars, red dwarfs, burn their fuel so slowly they can shine for trillions of years. So there will be stars twinkling for a very long time yet. But eventually, even those miserly red dwarfs will exhaust their hydrogen and turn into inert helium white dwarfs. Let's sketch the timeline. In about 100 billion years, the expansion of the universe, driven by dark energy, will likely have pulled all but our local group of galaxies beyond the observable horizon. Future beings in our galaxy at that time might think the Milky Way is the entire universe, as distant galaxies' light will have redshifted into oblivion. But stars will still be shining in our galaxy then. Fast forward to, say, 1 trillion, 10,012 years from now. By this time, most stars larger than red dwarfs will have long since died. New star formation will be a trickle. Much of the interstellar medium will have been either locked in remnants or swept out of galaxies. Some star formation might still occur from collisions of brown dwarfs,
or stellar remnants occasionally merging and sparking new stars briefly, but on the whole, galaxies will be dimmer. Red dwarfs, whose lifetimes can reach into the trillions of years, will dominate the starlight. They will be faint red glowworms where once splendid suns like ours shone. At around 10 trillion, 10,013 years, star formation will essentially cease. The reserve of gas for making new stars will be effectively depleted or too spread out. The universe's expansion will have put far-flung raw material beyond reach. The existing stars will run out of fuel one by one. The last truly luminous star might be a red dwarf finally flickering out. Imagine that far future night sky. From some hypothetical planet around one of those last stars, if planets still exist. Where once the sky was full of stars, now perhaps only a few faint red points pierce the darkness. Maybe globular clusters remain as isolated pockets of stars, slowly losing members to the galactic halo. The Milky Way, or whatever merged galaxy exists by then, our Milky Way might merge with Andromeda and others to form a large elliptical over billions of years. We'll no longer have the majestic spiral arms lit by young stars. It might be a huge ball of dark mass with occasional pinpricks of degenerate matter. When the last active star, likely a tiny red dwarf, finally exhausts its hydrogen, perhaps after 1014 or 1015 years, 100 trillion to a quadrillion years, it will expand into a small red giant, shed a bit of mass, then fade to a white dwarf. At that point, the degenerate era begins in full. The universe will be populated only by stellar remnants, white dwarfs, many of them cooled to become black dwarfs by then, neutron stars, and black holes, along with unbound planets, brown dwarfs, failed stars, and cold gas and dust. The average temperature of the universe will be dropping as well, as the background radiation is stretched to extremely low energies by expansion. What is life like in such an era? It's speculative whether life could find ways to survive around, say, a warm white dwarf, or on residual heat of a cooling neutron star, or by feeding off rotational energy of pulsars. Some scientists have pondered civilizations around white dwarfs, or even artificial habitats, feeding off black hole accretion disks, since black holes could theoretically provide energy via Hawking radiation or other mechanisms over extremely long timeframes. If any form of intelligence endures into these times, it would face ever-declining energy supplies. Time stretches on. White dwarfs gradually cool toward the background temperature, which itself might approach near absolute zero if dark energy leads to a de-Sitter space. On timescales of 10⁻19 to 10⁻20 years, most of the remaining planets will have either spiraled into their remnants due to gravitational radiation or interactions, or been flung out by gravitational encounters. The galaxy's shape will disperse as gravitational interactions over eons cause stars and remnants to scatter, some being ejected into intergalactic space, others falling into the central black holes. Around 10⁻20 years, 100 quintillion years, the Earth, if somehow it survived as a charred ember around the white dwarf sun, would either have been absorbed by the sun's white dwarf due to orbital decay from emitting gravitational waves, though that timescale is way longer than that for Earth-Sun, or more likely, the sun's white dwarf might have cooled to, say, a few thousand K, glowing faintly red. By 1025 years, definitely, any white dwarf like the sun's will be essentially a black dwarf, radiating at almost the same temperature as the cosmic microwave background, which itself would be incredibly cold then. To any remaining observer, these once stars would be effectively invisible unless you literally bumped into one. Over extremely long timescales, quantum effects might come into play. If protons are unstable, some theories predict a proton's half-life of 1034 years, then given enough time, all the atomic nuclei in white dwarfs, planets, etc., would eventually decay into lighter particles, like positrons and gamma rays. A white dwarf could slowly evaporate into a cloud of electrons, positrons, and radiation. If protons don't decay, another process can still thin out matter. Quantum tunneling could cause the iron in black dwarfs to fuse, or the object to collapse on unimaginably long timescales, 10 or 1500 years or more, or cause it to crystallize fully and just sit. One thing that will definitely happen in the far, far future is the slow evaporation of black holes via Hawking radiation. Black holes aren't completely eternal. Quantum mechanics suggests they emit a very faint trickle of particles and radiation, losing mass in the process. For a stellar mass black hole, the evaporation time is stupendously large, around 10^67 to 10^100 years, depending on mass. For the supermassive black holes, it's even larger, on the order of 10^100 years or more. But given enough time, even these leviathans will evaporate, each ending its life in a final burst of Hawking radiation that might briefly be as energetic as a small explosion. After that, nothing of them remains. As we approach times like 10 or 100 years and beyond, the universe becomes very quiet and sparse. All galaxies have dissipated. All black holes are gone. The particles left are mostly subatomic: electrons, positrons, neutrinos, and extremely low-energy photons, stretched out to absurdly long wavelengths. The expansion may eventually dilute even those, so that on average, you might have to search a volume larger than the observable universe today to find a single particle. The temperature of the universe will asymptotically approach absolute zero. This is the heat death of the universe, sometimes called the Big Freeze. It's a dark picture, endless space with virtually nothing in it. No starlight, no planets, no warmth, just the feeble afterglow of a cosmos that once blazed with galaxies. If consciousness or life hasn't found some way to circumvent the need for conventional energy, it would have long since flickered out by this stage. This is the ultimate endpoint of all the individual star deaths we've discussed. Everything ends, even the cosmos as we know it. Unless, perhaps this isn't truly the end. Some speculative ideas suggest that given inconceivably long times, random quantum fluctuations could produce a new Big Bang or a Boltzmann brain, a self-aware configuration of particles popping up by chance, though the time frame for that is mind-boggling. Other theories propose that our universe might tunnel into a lower energy vacuum state, essentially triggering a new kind of Big Bang that restarts things, though that would obliterate the current universe in the process. These ideas are currently beyond verification and wander into the realm of metaphysics or highly theoretical physics. For all practical purposes, under known physics, once the last black hole evaporates, the universe will be effectively dead for eternity, an ever-expanding, nearly empty darkness where nothing of note happens. This future is almost impossibly far away. It makes the lifespan of even the longest-lived star seem like a blink. Yet thinking about it can evoke a deep sense of existential awe. The universe had a beginning, and it may have an end. We live in a chapter, the chapter of shining stars and bright galaxies, that will not last forever. But it is our chapter, rich with story and meaning. Through this long exploration, a theme has quietly taken shape. In the cosmos, every death is also a form of creation. A star's death creates the chemical elements that may seed life. The remnants of stars lead to new phenomena, pulsars, black holes, that enrich the fabric of reality with their strange properties. Even the eventual fade of the universe sets the stage for who knows what. Perhaps a rebirth, perhaps a final piece. Philosophically, the story of stellar death resonates with us because it mirrors aspects of our own existence. We are born, we shine with life, we use up our days, and eventually we must go. But we are part of cycles larger than ourselves, biological cycles, cultural cycles, and indeed cosmic cycles. There is an ancient intuition in many mythologies that destruction and creation are two sides of a coin. From the ashes of the phoenix, a new phoenix arises. In Hindu mythology, the dance of Shiva destroys so that Brahma may create anew. The ancient Egyptians saw the sun die each dusk and be reborn at dawn. In the cosmic perspective, these poetic insights are quite literally reflected in the behavior of stars. A massive star perishes in a supernova, and from its remnants, new stars and planets will one day form. There's a continuity, an immortality of sorts, not for the individual star, but for the patterns and materials of which it was made. For most of human history, the stars were thought of as eternal and unchanging, the realm of the gods, or the perfect and divine, in contrast to the mortal, mutable Earth. Learning that stars are born and die has been a profound shift. It has united the heavens and the earth into a single tapestry of nature. The calcium in our bones and the iron in our blood are proof that we and the stars are intimately connected. The life cycle of a star is not fundamentally different from the life cycle of a flower in a field. There's a sprouting, formation, a bloom, main sequence, a withering, giant phase, and a scattering of seeds, nebula and remnants, to ensure the next generation. It's just on a much grander stage and longer timeline, but the pattern is familiar. We see it in our own lives and in the ecosystem around us. What meaning can one take from this cosmic perspective? Some might find it nihilistic. Everything ends, even starlight dies, and in the far end, nothing remains. But one can also find it deeply inspiring. Death in the universe is not a permanent annihilation. It's transformation. The end of one thing is the beginning of another. The universe wastes nothing, rearranging dead stars into new stars, dead galaxies into new galaxies, on larger scales through collisions, perhaps dead universes into new universes if some theories hold weight. If even the stars, those eternal lights in the sky, must die, then how remarkable it is that out of their death comes something as poignant and wonderful as us, beings made of their dust, able to contemplate the very process that gave us form.
There is also a lesson in humility and gratitude. We gaze at the stars often with a sense of permanence. They seem the fixed backdrop of our lives, but they are on their own journeys from birth to death. We happen to live in a cosmic age rich with stars. It will not always be so. This recognition makes a clear night sky even more cherishable. We are witnessing a phase of the cosmos that, however long, is transient. We are fortunate to see a universe awash in light. The darkness that will come is beyond our personal timescales, but its inevitability makes the present cosmos no less splendid, if anything, more. Above all, the death of stars teaches us that endings can be creative. The stars do not simply vanish, they leave behind gifts. They forge the gold in our rings, the oxygen in our lungs, the silicon in the rocks beneath our feet. They leave behind neutron stars that keep time better than atomic clocks, and black holes that test the limits of physics. Even in their violent final acts, there is a profound generosity. They give themselves to the universe. We too are of star stuff and will return our atoms to the greater pool. In a poetic sense, one could think, as we live, we are a way for the universe to know itself, since our brains are made of those very atoms forged in stars and now contemplating the cosmos. In dying, we give those atoms back so that new forms, new consciousness can one day arise. It's a scientific truth that every atom in our body will outlast us, moving on to become parts of other organisms, the air, the ocean, and over geological time, part of new minerals, or maybe subducted into Earth's mantle, or blown out to space if Earth loses some atmosphere. On very long timescales, perhaps our atoms will cycle through new planets, or even be lofted off Earth when the sun dies. It's a kind of immortality, material, not personal, but comforting in its continuity. As we near the conclusion of our journey, step back and look at the night sky again,
perhaps in your imagination if it's not visible right now. See the stars twinkling. Look up at the night sky and breathe in. Feel the air enter your lungs. That air contains oxygen that was created in a red giant star billions of years ago. It contains nitrogen that may have been produced in some long ago stellar factory, carbon from another. The iron in your blood was born in a supernova explosion, traveling through space, eventually finding its way into the cloud that made the sun and planets, and then into your body. Every breath is a connection to that stellar heritage. As you exhale, perhaps some of those atoms will return to the atmosphere, and a plant will take them in tomorrow, incorporating the carbon into a leaf. Years from now, that carbon might be part of a fruit, eaten by another person, and become part of their body. And so the cycle goes on Earth, small echoes of the greater cycle of stars. We are all connected through these cycles. When we gaze at a distant star, we are seeing it often across a great span of time. The light reaching our eyes might have left that star hundreds or thousands of years ago, before the rise and fall of nations, before any living human. In that sense, to look at the stars is to look into the past. We are literally witnessing ancient history. Some of those pinpoints of light are from stars that have already died, their light only now arriving. The cosmos is a memory machine, preserving in the speed of light the images of the past. The night sky could be seen as a grand memorial of stars, some alive, some long gone, but all appearing together to us as if coexistent. We remember the stars by their light, and in turn, we carry the stars' memory within us because we are made of their remnants. The universe has enabled us, beings of matter, to evolve and eventually understand this very fact. Through our studies and stories, the cosmos is remembering itself. Our knowledge of stellar evolution is the universe's self-reflection. We, tiny, ephemeral humans, have figured out how stars live and die. We've collected the whispers of ancient light and decoded the messages of neutrinos and gravitational waves to fill in pages of the cosmic story. In so doing, we are giving voice to the stars that cannot speak for themselves. We are eulogizing them even as we celebrate their role in giving us life. When you next find yourself under a clear, starry sky, take a moment to feel the depth of time and the cycles at play. That band of the Milky Way is the combined glow of billions of stars at various stages, some just being born in nebulae, some shining in middle age like the sun, some swelling into red giants, some already collapsed into remnants hidden in the mix. Perhaps one of those stars will explode tomorrow and be seen by us in a few thousand years, given distance. Perhaps around one of those stars, new civilizations will one day come to be, using the elements those stars provide. We are not separate from this grand cosmic web. We emerged from it. We return to it. There is a profound kinship in knowing that the carbon in your cells was forged in stellar hearts. It binds us to the universe, to the stars that died so that we might live. This knowledge can influence how we see our own lives and deaths, not as isolated events, but as continuing contributions to an ongoing story. Just as a star's death enriches the galaxy, maybe the mark we leave, through our actions, creations, and children, or at least the literal atoms of our body, enriches the tapestry of humanity and life. And so, the death of stars is at once an end and a beginning, destruction and creation fused in one cosmic act. It is a beautiful paradox that the universe appears to operate. Nothing lasts forever, yet nothing is ever truly lost. The atoms always cycle through new forms. The energy finds new channels. Even black holes, which hoard matter and energy, eventually give it back when they evaporate. This journey has been long and filled with wonders. From the quiet death of a sun-like star casting a glowing nebula, to the explosive demise of a supergiant birthing neutron stars and black holes, to the mergers that ripple space-time, to the ultimate fate of a cosmos drifting into darkness. Throughout, we find echoes of our own existence, and perhaps guidance for our own lives. We learn that great energy and growth, like a star's main sequence, eventually yield to change and aging, the giant phase, and finally to transition, death. But we also learn that what comes after can be meaningful. A star becomes a white dwarf that may one day spark a nova and bring new light. Our lives might influence generations ahead in ways we cannot imagine.
Under the eternal night, we contemplate these things. The stars do not last forever, but their story does, written in us and around us. In the endless night, we remember the stars, and through us, the stars remember themselves.